So, good morning, everybody. My name is Czeslaw Bruckner. I just learned that I'm promoted to a chair of this session. So, the first talk is for 40 minutes. It will be given by Hing-Tong Cho, and then we will have some ample time for the discussion. So, please.
Thank you. Thank you for the introduction. Well, good morning. I'm happy to see you here after the dinner last night. Well, first, I would like to thank the organizers to give me the opportunity to present my work here. So I'll talk about graviton quantum noise, basically, and its influence on particles, either classical or quantum. And this work is done in collaboration with Baylock, who's in the audience. Sorry. Okay, so the references for this project you can find in the past few years. You can find it here. So, well, the one that the last one was out only a couple of months ago. So this is the outline. So I will first say a few words about motivation. Okay. And then I'll introduce in some detail the Brownian motion model because it is a simple model, but it has all the characteristics of the formalism that we are using when we applied it to gravitons. Okay, so then I will apply this formalism to gravitons and see how the quantum noise emerge. And then to look at its influence on particles, basically classical particles, I'll first look at what is called the Langevin equation of motion for the particle. And then if the particle itself is considered to be quantum, then I would have to look at the master equation for the reduced density matrix. Okay, and then at the end, I'll give some conclusion. Okay, so motivation. Okay, so well, everybody knows that after 2015, gravitational wave has been detected by LIGO. So after this, well, I mean, research in gravitational wave exploded, I suppose. But people, well, in this audience, it won't be, it is apparent that everyone, well, I mean, people try to find ways to look at the quantum nature of gravitational wave or graviton. Okay, and there are many proposals, you know, presented also in this conference, but there is one that was given or proposed by Wilczek and collaborators like a few years ago through the study of quantum noise, okay, of graviton, okay, and the approach is actually that of an open quantum system of Feynman and Vernon, okay, so. So that's why I would, well, I mean, say in some detail the approach. And, but actually this approach was quite old. It was first applied to graviton by Gali, Hu, and Lin. Xiyun Lin is also in this audience. So they first applied this to graviton actually something like 20 years ago. Okay, so this is not new. Okay, so let me first start with the Brownian motion model, which is very simple. We have a system which is basically a particle. So we have the particle action with the potential. And then for the environment, we consider it to be a set of harmonic oscillators. Very simple. Okay, so you have Qn, the degrees of freedom for the harmonic oscillator with omega n, the frequency. Now, the interaction between this system and environment is given by this bilinear interaction. Okay, so because it's bilinear, so it can be solved exactly, basically. Okay, so that's why it's considered to be a very simple model that you can explore the characteristics in full. Okay, So, well, I mean, this model has been considered by many people, notably Schwinger, Feynman, Vernon, Kader, Leggett, and also by Hu, Pass, and Chen. Okay, so I'll talk about that in a moment. Okay, so what we start with is we try to look at the in expectation value of the system, okay, or wherever, either quantum or classical, basically quantum. If the quantum, then we look at the in correlation functions of this. And to do that, we need what is called the closed time path formalism. Okay, so you have, basically consider that there are plus fields and minus fields. Plus fields go forward in time, minus fields backward in time. And then there is appropriate boundary condition at final time, okay? So now we try to integrate over the environment degrees of freedom for this open system approach. So to do that, we integrate over this Qn, degrees of freedom, okay, using this path integral. Okay, basically I'm using path integral formalism. And to, sorry. The cable. Oh, it comes now. Okay. And it's not. Oh, okay. And maybe I don't use this one, or it's not related. Oh, okay, okay. Not this computer. I have it in my computer. Yeah. See if it works. Yeah. No, here. Yeah, you have to use this one. Yeah. There's another port. Right here. See it? Yeah. Is it? So it's not the computer. Yeah, okay. Thank you. Okay. Yeah, let me continue. So if I integrate over the environment degrees of freedom, then I will arrive at so-called inference section. Okay. So basically, I integrate over the environment degrees of freedom. Then all the inference of the environment to the system is basically encoded in this inference section. Well, since the interaction is bilinear, so you can see that it can be integrated completely, and you get something quadratic in x plus and x minus. Okay, so these are the so-called Stringer-Kaldis Green's functions or propagators, and they're basically time-ordered or anti-time ordered Green's functions and or the positive and negative Wightman functions because of the boundary condition that we chose. Okay, so in this simple model, you can these propagators can be calculated completely and with this real pi by this. Okay, so I'm not going to go into the details, but then the inference section can be more apparent. I mean, its structure can be more apparent if you define the difference of x plus and x minus at delta x and also the average of the two. Then you can see that the inference section will be separated into real, again, real and imaginary part because the Green's function itself is separated into a real and imaginary part. Sorry. Now, the Feynman-Vernon approach comes into this in a rather simple trick. Okay, you can see that this real, real part of this exponential is delta x squared with nu, the kernel nu, and if you you just complete square basically. You complete square and introduce a psi field. Then you can put it into this form with a Gaussian probability density. So psi field becomes a stochastic field, okay, or stochastic force. And since nu itself is the correlation function of this force, so that's why it's called the noise kernel. Okay, usually. Okay, now if you use this effective action, and then as I said, you have the inference action with this eta, which is delta x, sigma x, and then you change the delta x squared into this, using this stochastic force to make it into actually a linear term with delta x. Okay, but then you have a path integral or integration over this psi stochastic field. Okay, implicitly here. Okay, so if you want to look at the equation of motion, you take variation with respect to x plus, and then take them to be equal to x and equal to 0. Then you get what is a Langevin equation. Okay, basically you have this stochastic force term on the right-hand side, which that's why it's Langevin, and then you still have this eta term, which can be turned into actually a dissipative term. If you look, you can change this eta as the time derivative of gamma, and you put it back, then you can see that it's proportional to velocity. So it's basically a dissipative term, but it is history dependent, non-local. Okay, it's a non-local dissipative term here. So you can analyze the system if it's classical through this Langevin equation of motion. Okay, so that's why eta is called the dissipation kernel. Okay, so you have dissipation kernel, noise kernel, which is related actually to the Green's function and which is also related to this inference action. Okay, so if the system is quantum, then we need to look at its density matrix. And if you integrate over the environment degrees of freedom, you basically arrive at the reduced density matrix. Okay, so its evolution is governed by this reduced evolution operator for the reduced density matrix. And if your initial density matrix is separable into environment degrees of freedom and also system degrees of freedom, then in this model, the integration over the environment degrees of freedom can be done completely again because it's, bilinear. So, and then, as I said, you arrive at an expression which is for the evolution operator for this reduced density matrix in this path integral over x plus and x minus, okay, with appropriate initial and final value, okay? And, it's a long calculation, but at the end you can arrive at the master equation, which is now called the HPC master equation with, you can see this is the gamma, which is the dissipation coefficient, sorry. And dpp and dpx would be the diffusion coefficient responsible for the coherence, okay? So that's the formalism for Brownian motion model. Now I applied it to graviton, okay? So actually all the characteristics would be similar, but it's just in a more complicated setting. Okay, for the graviton, I would start with the Einstein equation, and then if I perturb it about the Minkowski background for simplicity. Okay, in principle, you can do it in any background. For example, if you're interested in cosmology, you probably do it in a de Sitter background or Roberts-Walker and so on and so forth. But I'll do it in a Minkowski background. Then basically the lowest term turn into a action for two minimally coupled scalars. Okay, so because you have two polarizations, and you arrive at two minimally coupled scalars, and for the particle itself, it's a particle, so I start with the action for this particle, and for my case, it would be actually in the Wilczek collaborator model, they choose the Fermi normal coordinate in which one of the particle is supposed to be the time axis, and then the nearby particles would be can be described in this normal coordinate. Okay. In this case, I can expand, and basically you have a kinetic term, okay, for the particle, and then you have an interaction term between the particle and the graviton, okay. But the important thing here is not bilinear anymore. You can see that is linear in H, but then it's quadratic in Z. Okay, so the complication comes in this form. But since it's, at least in this, in this lowest perturbative order, is linear in H. So in that case, we can actually calculate everything, the noise kernel or the inference action in full. Okay, basically in this perturbative order. So you do the same thing as before. You integrate the graviton field. Well, with two polarizations, so there will be a tensor structure coming in, and you would arrive. Okay, you will arrive at this inference action with the dissipation kernel and the noise kernel again. And because it's quadratic in Z, so you can see that my sigma and delta would be in this form rather. Okay, so the noise kernel and the dissipation kernel, the dissipation kernel will be given by this retarded Green's function, okay, for a minimally coupled scalar, okay. And for the noise kernel, it would be related to its Hadamard function, okay. So they come out with the boundary condition that you choose, okay. So everything we can completely calculate this. You can see that I have the polarization tensor for the graviton here. You have some tensor structure. And then using the Feynman-Vernon trick again, then you can turn it into a stochastic force. But now the force itself is tensor. Tensor is a stochastic tensor force here. So with psi ij, okay. And then you also have a Gaussian probability density. Okay. So everything looks almost the same as before. Now you arrive at this, what we call a stochastic effective action with the dissipation term and the noise term turn into this stochastic force. Okay. Well, implicitly there would be a path integral over this stochastic force. Okay. Here. So if you want to look at the classical its influence on the classical particle, then you look at the Langevin equation of motion for the particle here. So you take a derivative with respect to c plus, and you arrive at this. Yeah. So you would have again a dissipative term, okay, and also the stochastic force term. Okay, it would be similar to what we had before for the Brownian motion model. Now, we try to analyze this Langevin equation to see what is influence on the particle, how for example, the fluctuation of this geodesic separation would be because of the effect of this quantum noise. And in doing so, then we concentrate on the force term. So we neglect the dissipation term. We concentrate on the noise term. And remember, is the expectation value of the tensor force would be related to the noise kernel. Okay, so you have, well, I mean, since it's quadratic in C, so you still have the tensor force term times Z. So you basically have this kind of Langevin equation motion. Okay, solving is not simple, but it's easier if we assume that the fluctuation is small. Then I would have a Z0, 0th order, and then a fluctuation, and the 0th order would be like the one without any graviton effect. Okay, so basically a line, okay, for us in the Minkowski space. So if I calculate, using this approximation, calculate the fluctuation, then it would be proportional, basically proportional to psi KL and also Z0, which is the separation without graviton effect. And if you look at the correlation of this fluctuation, then it would be proportional to the noise kernel. Okay, you can imagine, because of the stochastic force terms. Now you can estimate. How big is the fluctuation, and well, if you look at just the Minkowski vacuum, you can really expect that it is of the order of the Planck length. Okay, so you're not expected to be able to detect this. We also look at different vacuum. For example, we look at the thermal state. For low temperature, it's proportional to T cubed, and high temperature T to the 5/2. So for the high temperature, maybe, but it has to be very high temperature to be enhanced. But the most interesting one would be the squeeze state. Okay, we look at the squeeze states, and this would be have squeezing for all modes. I mean, same squeezing for all modes for simplicity, and the squeezing parameter is zeta. And you can see that the fluctuation would be proportional to exponential zeta. So since for the squeezed graviton, I mean, I think people now understand that in the early universe, especially in the inflationary model, the graviton created would be in a squeeze state. Okay, so depending on different models, you have different squeezing. And well, I mean, there's one model, I'm just squeezing to the order of 10 to the 18. In that case, then the fluctuation, I mean, it would be enhanced to such an extent that it might be detectable. But that's for primordial graviton, so maybe, well, our calculation actually is in Minkowski space, so maybe you have to repeat the analysis using, for example, de Sitter space, okay, to be fair, yeah. So we have done also for, well, since it's a geodesic separation, you can also look at geodesic congruences with, well, I mean, different parameters, expansion scalar, shear tensor, and rotation tensor. And since graviton is, well, I mean, is transverse traceless, basically, only the shear tensor would be affected, okay, by the stochastic force. Okay, so I'll just go to this because it's the same conclusion that for a squeeze state that would be enhanced by this factor. So I mean, similar conclusion. Okay, for the shear tensor. Okay. Now, our recent work would be on if we look at the system to be quantum. Okay, so we look at the density matrix. Okay, actually the reduced density matrix for the particle, and we assume that well, I mean initially they're separable, and then we can do the integration over the graviton degrees of freedom in full, and then we can arrive at this evolution operator. Okay. So basically, again, this operator would be path integral over z plus z minus with this action. Okay. So inference action again. Okay. Now we suppose that we have the inference action, then we can put it back in and then do the integration. Well, it's easier said than done, but yeah, so we have this inference action again, and then, well, basically you have to change this to sigma and delta, okay, rather than ij. And then you do the calculation, okay, so it's a rather long, lengthy calculation, but at the end you arrive at this master equation. Okay, but one thing I should mention is that right here. So, or here, because you can see that I have to integrate over x plus and x minus. Now, in this case, we have quartic terms for x plus and x minus now, rather than quadratic in the Brownian motion model case. So we cannot do it in full, of course, so we resort to perturbation again, okay, for this. So we have to expand this exponential and then do perturbation. Anyway, so in the lowest order, we can arrive at this, basically at this master equation, which is quadratic, okay, so you can see these terms, oh, the D1 and to D4 are terms related to the dissipation kernel, and N1 to N4 are those related to the noise kernel. Okay, so you can see that we have quadratic terms here, and also quadratic terms coming from graviton interaction. And the quadratic term basically can be considered as some kind of renormalization. So we would concentrate on the quadratic term, okay, and so we can see that the quadratic term would be would be terms, okay, related to N4 and D4, and the N4 term, the noise term, would be related to decoherence, okay, and the dissipation term related to processes which has loss of energy, okay, so because it's dissipation term. Okay, so I mean, it looks simple, but it's actually quite complicated one if you look at it in generality. But I have to emphasize that people have considered this before, but then usually in some like high temperature approximation. Now this is, well, within the approximation they were doing, perturbation, I mean, the approach that we're doing is for all temperature, okay? So it's for all temperature, but if you look at the high temperature limit, okay, so beta is 1 over T, so beta goes to 0. Actually, one arrive at the so-called Markovian limit, okay? Why? Because the noise kernel itself will be proportional to the delta function, okay? But at least at the lowest order, okay? So this is, this case has been considered before, actually, by, well, I'll show you. So you can, the master equation, okay, with the noise term can be reduced to this kind of form. And you can see that it actually it tells you that there is decoherence for the off-diagonal elements, okay? So the decoherence time scale, okay, would be proportional to this constant. If we use momentum representation, then it can be written in this form. So it's, well, I mean, it's perturbation, so alpha basically is the graviton coupling, and alpha square, and then it's proportional to the 1 over beta, so it's proportional to the temperature T, and this momentum. So this result has been obtained some time ago by Brankov and Anastopoulos and Hu. So basically we call it the ABH equation. So in this approximation, okay. Now, so our equation is actually, valid for all temperatures. So we can look at some other limits. For example, the low temperature limit, then the noise kernel would be, the temperature part would be T squared, would be proportional to temperature squared, rather, okay? And if you put it back into the master equation, then the temperature independent term would be 1 over T, time, T is time now. And then this temperature dependent term would be proportional to time, okay? So A is a constant, as before. So if you analyze this, you can see that the temperature independent part goes like minus log T, okay? The decay, okay? Decay of the off-diagonal terms. And for the temperature dependent term would be like minus T squared, okay? Time, okay? Small t squared. And itself is actually also proportional to the temperature squared, okay? So it's very different from the high temperature limit here, okay, maybe here, which is proportional to T, okay? So we have a rather different behavior in this low temperature regime. So I think that, because the noise kernel itself is not proportional to the delta function, so it's basically non-Markovian, okay? This behavior should be non-Markovian. So, and it has a very distinct properties than that of the high temperature Markovian limit, okay? So I think this is a conclusion. So we consider the quantum effect of the graviton through its noise, okay? So we try to find the influence of this noise to classical particle motion, like fluctuation of the separation. We study different RQI, Minkowski, thermal, and squeeze states. Maybe squeeze states would be more promising, as I said before. And similarly to the fluctuations of the circumferences for the other, for shear tensor, basically, okay? And if the system is quantum, then we obtain the master equation. So we still need to analyze the equation in more detail, but we can see that in different limits how it behaves. Okay. So thank you for your attention. I'm done here. Yeah.
Thank you. So thanks for your talk. Just a question, if I do the analogy to electrodynamics, would you say then the electron is kicked around by the quantum vacuum fluctuations of the photon field? Or is this just some well-known effect like the electron mass renormalization? Or if you draw this analogy, how would you explain it?
Yeah, basically it's the same. I mean, we have graviton in the environment, then you have photons in the environment. Yeah, I mean, we have...
Same vacuum, in vacuum
Same
case.
principle, yeah, same principle, yes. Yes, basically.
Okay.
Yes.
Okay.
Yeah.
Thanks for the talk. I have a question about covariance, because you fixed coordinates before everything else. But this assumes an anomaly-free path integral measure over matrix, which I don't think it's known if that exists. So did you try different coordinate choices and see if you get similar results?
Yes, I have chosen the Minkowski. Basically, background spacetime is Minkowski. So yeah, I have chosen a gauge. The traceless, the transverse traceless gauge for the graviton. So in this way, I'm fixing, the gauge. Yeah, and then quantize. So, but I think is relevant to the lab experiment data. So yeah, if that's your question, yeah.
Thank you very much for this very interesting talk. I would have a short question. You consider different limits for the environment, like the low temperature, high temperature limit. Can you already comment from this which kind of graviton environment would be most favorable to kind of maybe detect such a decoherence effect? So would it be like rather an environment which has a high temperature or a low temperature with this interplay with the dependence also on the time?
That one I really cannot say, okay, because we got the master equation for all temperatures, and then we look at different limits. Okay, well, basically for the high temperature limit, it has to match with the ABH equation. So they just have different behavior. I don't know in which laboratory setting would be easier to detect, but for example, the low temperature limit, we expect if there is some experiment that is of low temperature, that kind of thing, then would be, that can see a different behavior than the high temperature one. So it's just that. So for really experiments, I really cannot say, yeah.
Any further questions? I may use an opportunity. So I have more general questions about decoherent spaces. So you showed that in that case, the coherent spaces, the preferred basis of decoherence would be momentum.
Right.
So usually, when we think about non-relativistic physics or attempts to understand classical limit, we have decoherence mechanism with preferred position basis. Right. That's somehow we then argue, well, the systems are localized, and that's how we see them. And now, a momentum basis would allow, it's usually non-local measurement.
Okay,
You have a non-local measurement. That's good. And so my question is, would this still allow delocalization in space that it sounds like that the decoherence in momentum would allow delocalization in space. Actually, not only allow, it will necessitate if you make a very sharp measurement in momentum. So,
well, okay, yes. For that question, I really cannot comment on really, because we have not looked into. But I think in momentum basis or momentum representation, because we are looking at graviton interaction, so it's basically related to energy. So that's why it would be much more related to this momentum representation.
I understand why it is.
Yeah. But for your question for the localization, I really cannot tell. Yeah.
Okay. Thank you. And thanks to speaker
Sure.
once more.
Thank you so much. Fine, nice to see you again. One second.
Because I was not supposed to be so
Only 30 minutes, right? Minus 30.
Do you want to warm it 5 minutes before, like 25?
Yeah, that would be wonderful.
So here is your water. There's more if you...
Thank you.
Does it work?
Yeah, actually, if possible, and you could also warn me 10 minutes before, no?
10 minutes, yeah.
I'm getting older, I keep on going and going and going.
So after 20 minutes, 10 minutes before, I show you 10 minutes.
10 and 5.
And 10 and 5.
So is this not the microphone?
That's for the streaming and that's for the audience.
Ah, okay. Okay. Can we, just in case that this doesn't run out of power, can we plug this in as well?
That's the problem. The
No
the
plug.
power is on the other side.
Ah.
Okay, so our next speaker.
Okay. I mean, if it comes to it, then maybe we're lucky.
We'll talk about quantum simulators for whatever it was there. Fundamental physics, quantity, fundamental physics, yes. Okay.
Okay. Thank you. Also, thank you to the organizer for inviting me here. It's absolutely stunning, very beautiful, a bit warmer than in the UK. I'm going to talk about quantum simulators for fundamental physics, but today there are two very simple take-home messages which I want to get across. And the first one is the experimental challenges to set up rotating black holes in the lab. So this will be focusing on analog simulators for black holes, and I'm going to motivate that as well. And why do we need to do this in a quantum system? So these are the two take-home messages which I hope you will take home from my presentation. Okay, so first I think we should motivate why quantum field theory in curved spacetime. Perhaps this is a convinced audience already, but there's really a lot of fundamental physics at the intersection between generativity and quantum field theory. And these are essential processes where theory, observation, or experiment offer limited or no access. Okay? So, and there are cases related to the dynamics on cosmological scales. There's a quantum vacuum and relativity, such as the Andrew effect. And what I'm going to focus on is black hole interactions with classical and quantum fields. Right. So since there is so limited access or observational access, what I'm focusing on is analog quantum system or gravity simulators. And the idea is to recreate some of these complex quantum phenomena in the lab. And this is to explore this fundamental physics that is otherwise hard or impossible to access directly. Okay. So this idea goes back to, perhaps if I had to choose a single paper, the idea goes back to 1981, when Bill Unruh realized that there is an analogy between two completely, or at first, completely different physical systems. The one he was concerned with where you need a gravitational field, and in particular looking at field propagation around a black hole, for example. And on the other hand, he looked at fluid flows, which are described, for example, here with a three-dimensional flow velocity. So these two things at first have nothing in common. But the analogy comes apparent if you focus on small fields or excitations in the two systems. And the first system is you look at sound waves in this fluid flow. And in particular, if you put a little speaker in here and you look how sound waves propagate, you will see that if you have a background flow that accelerates as you go down here, go down a waterfall, for example, you see that the sound waves propagating, let me go back. Let me see. So the sound waves propagating with the flow propagate faster than the sound waves propagating against it. If this waterfall keeps on accelerating and you have a little speaker here, what you see is that this sound waves here emitted on an area, when you define an area where the background flow is equal to a perturbation speed, all the sound waves get dragged downstream. So that is sort of the basic theoretical idea, and of course you can map this out more carefully. And what you can do is you can say, well, everything that is below that point of no return for sound waves can be enclosed here, what's called an acoustic horizon, if you work with sound waves in the system. So this was the basic idea, and my talk will be about how can you realize this in an experiment. So before going into this, I want to point out some of the derivations of the analogy and what exactly is the analogy. And so when Bill sat down, and worked out how sound waves propagate in such a fluid flow, he made some basic assumptions. And the first one is, well, I have a density, but I'm assuming it's barotropic, and I have an inviscid and irrotational velocity field. And because of that, I can write my velocity field as a gradient of a scalar field. So these assumptions are quite critical to derive this analogy. And because it's barotropic, you don't really have a pressure, because the pressure is a function of the density. So you have these two parameters, these two scalars, which is the density and the irrotational velocity. And then if you look at the fluid equations, you have the continuity equation and the Bernoulli equation. And what you need to do to map this onto black holes, you need to look at small perturbations, as I said. So you perturb around the density and the velocity field. And if you do this, you can rewrite the set of equations that you get in a single equation where you have a relativistic wave equation for the velocity perturbations for this field here. And you do this by introducing an emergent or effective spacetime geometry. And this geometry has a background velocity v and a propagation speed c here for the sound waves in the system, for example. So this is all straightforward. And it's just a different way of conceptualizing the dynamics of the sound waves in the system. And you can introduce a mapping. You say, well, the speed of light now is the speed of sound. The field here is the velocity perturbation. And the conjugate momentum is simply a density perturbation. And that's the whole atlas. This is the mapping. Now, of course, as often when theorists derive something, this is highly idealized and simplified. So as time progressed, people started to realize that actually this is not just valid for sound waves in fluids, but also for sound waves in air and liquids, sound waves in quantum gases and liquids, and interface waves on normal and quantum liquids. So everywhere it occurred, and of course, the answer was already in the derivation why this would be ideal to map onto quantum fields or quantum liquids, because you're basically treated your normal fluid as a quantum fluid, an ideal fluid. So there seem to be this plethora of systems that all end up having the same dynamics. And the first question that we asked back then, does this really work? So and to show this or to investigate this, we used the worst system in a way. We used the one that violated these conditions which you derived in it the most. So we worked at liquids at room temperature. So how does an experiment look like that? So you are having what's called an open channel flow. It's something that you find in every civil engineering department. And so it's a very simple setup. So here I have a water reservoir, you have a water pump that pumps it through into this upper compartment here. You go through here a series, it's called an intake reservoir, and you put some flow straighteners, and you send this through this open channel flow. And then what you insert here, you insert this obstacle. And this obstacle is all you need, and then it has to be some careful design how to place this into the flow, but you have basically water flowing through. At the end of your tank, there's a wave generator where you can send waves upstream, and then the water goes down in the intake reservoir, and the whole thing repeats. So why is this suitable to set up an analog black hole horizon? Well, what we focused on, and this is the first message, is not sound waves in the system, because sound waves in the system would require that you speed up your fluid flow to very high velocities, thousands of meters squared. But here, for these interface waves, which we're looking at as the little ripples on the free surface, they scale with the height of the fluid flow. What is important for the analogy is that you work with large systems, that the waves you consider are large compared to the depths of the flow. So that's another complication that comes in here working with normal fluids, because you can't make them too thin, because then boundary effects are dominating. So again, here what you do, while the water goes over the obstacle, it accelerates, and it sets up a pair of horizons. You have a black hole horizon upstream and a white hole horizon downstream. Now, while one point I want to make here is that this horizon is naturally occurring in riverbeds, so it's something very tangible and easy to set up. And so this was the first experiment when we then probed these horizons to look for signatures of the Hawking effect. Now, what I want to focus on is on setting up hydrodynamic rotating black holes. So if you want rotation, you need to add rotation to the system. Hence, you can't really work with a one-dimensional open channel flow. So instead of that, you need to add rotation. And the idea is that you have a two-dimensional velocity field. It has a radial and an angular velocity component. So how do you get horizons out of this? Well, you have these effective horizons in the system. You have a black hole horizon when the radial velocity is equal to the speed of the ripples on the free surface. And you have an ergosphere when the total velocity, the radial squared, and the angular velocity squared is equal to your interface speed. Okay, again, this is the simplified idea. This is the basic way of mapping how you could potentially get to hydrodynamic rotating black holes. So when you do the math and you follow this perturbation approach and you linearize height fluctuation, not density fluctuations in this case, and velocity field fluctuations, you can write down an effective metric which contains this two-dimensional velocity field. Now, how do you set this up? So the idea was, well, I set up an open channel flow which allows for rotation, but instead of moving the whole thing on a rotating table to add rotation to the fluid flow, we did something different. If you look at that, we have here this open channel flow. It has a sinkhole in the center that can be exchanged with different geometries for the sinkhole. And you have these two inlet arms. And these inlet arms are placed in a way that when the fluid goes in, it gives it an angular momentum. It pushes it. So it starts rotating the flow. And these inserts here are to demonstrate you how you can go in, and then the flow would start rotating anti-clockwise. This is how it looks like. Warping comes simply to get the whole tank onto a single image. But the whole system is 3 meters wide and 3 meters long and 1 meter 50 wide. So, and this is what you can get. You can set up nice vortex flows of varying sizes depending on how you choose your inlet parameters and your sinkhole geometry. Now, how easy is this really? And it's something I think I never really explained often enough or detailed enough. What are the complications of having a system like that and mapping it to your rotating to quantum or classical field dynamics around rotating black holes. So here our target system is a rotating black hole, which should ideally be described only with this metric or effective metric tensor here. On the other hand, what I set up from a fluid perspective is a stationary draining fluid flow. Now here's a problem, that this stationary draining fluid flow are complicated and beautiful structures. And what does this mean? If you look at this, a recirculating flow, so a stationary flow that has a sinkhole in the center, what this means is you have the flow behavior is very unexpected. So you have a vortex core, and you have a bulk flow around. And in this bulk flow, nothing is draining. So how does it drain? Well, it drains through the boundaries. It drains through the top, and it drains through the bottom. And these are called the Ekman layer boundary condition, or Ekman upwelling, for example, on the bottom. And why is that? Because the flow comes around. It comes around on the top and on the bottom. It doesn't drain here in the center. But what happens when it hits the core, it can't directly drain. Instead, it goes up, and then it goes down, merges with the thing on the top. And this is how these bathtub vortex flows work. So, in other words, there is an irrotational part outside in this bulk flow where you have a nice angular velocity profile, very little radial flow. But in the center here, all the vorticity is contained in the center of the flow. And so one of the big questions was really, if I set up a flow like that and I have vorticity in the center, in the core of my vortex flow, which also gives birth to additional degrees of freedom, in fact, what it means is that the analogy wouldn't be ideal. And that's something to test in experiment if this indeed could still be used as a hydrodynamic rotating black hole simulator. So this is how we did it. And that just shows you have some wave generator on the side, and just to show you what kind of structures you're getting. And the first thing we did is we looked at a coherent wave interacting with your vortex flow. And the question was really, can I describe this wave propagation through, for example, geodesic motion? Okay. And what we designed the experiment for in particular was to see if you probe this vortex structure with a particular kind of wave, so the right kind of wave, that it can steal some of the black hole's rotating energy. And so how does this work? You have an ingoing wave, and let's assume you normalize the amplitude to 1. And then this wave impinges on the rotating black hole or your vortex geometry, and instead of draining, it comes out, and it increased its energy. So far away from this geometry, I look at the reflected amplitude of the wave, and it's more than I sent in. So it's not just an elastic scattering process, it's a super radiant scattering process. Now, this is a bit the story of David and Goliath, where David is fighting with this black hole. It's this tiny wave that actually can, by interacting with this vortex geometry, can reduce its angular momentum. Okay, so we did this. We looked at coherent waves interacting with this vortex flow. So we carried out scattering experiments at different frequencies. These are the patterns you get. And you can analyze these patterns. You can look at the frequency over the reflection coefficient, where the ingoing amplitude is normalized to 1. And what you can see, if of course this is going above 1, you have this super radiant scattering process. And the right kind of waves here are the ones that are co-rotating. Okay, so this is the story. Another thing that we looked at in this vortex flow, we noticed that there's a lot of noise around these vortex flows. And this gave us an idea to look at something that happens around black holes. And in particular, if you have a black hole, you perturb it, or you follow what happens after two black holes are merging, you will see that they give off some waves. And these waves, of course, as you know, that we detect here on Earth through, for example, LIGO gravitational wave detectors. And so what is happening here is you have these two black holes, they come closer, they're in spiral, and they start merging somewhere around here. And at the end of this, you have a newly born black hole that is the sum of the two, a bit less because also gave off some energy through gravitational waves. But then what you see, you have this final phase here, it's called the black hole ringdown. And this black hole ringdown is important because it probes the gravitational field around the newly formed black hole. And in our case, the effective flow potential of the vortex flow caused in the system, if this effect occurs. So this is what we're interested to see, and we also wanted to see if these ringdown modes are indeed excited. Okay? So this is what we saw. We saw a lot of noise in the system around that vortex flow. We made this vortex a little bit unease. We put it out of the stationary state and let it relax back. And then we did an analysis. And what we realized, we found what's called the fundamental modes in the system. This is fundamental modes for different orbital spin waves in the system over a range of frequencies. And the green dots here are the data with the error bars, and the black one is the prediction, looking at the background flow and using the whole procedures developed in gravitational waves to predict these ringdown modes. So these are the classical experiments, and they work quite well. And the question is now, how can you extend this to quantum liquids? And there's a problem you need to overcome, and I tell you how we overcame this problem in the first hand. And the second hand, I want to tell you how, by working with an ideal fluid, how much more you can get out of these two cases that I just shown you in the classical system. So the fluid of my choice as a quantum simulator is superfluid helium-4. It's a macroscopic quantum state that's very important here. So that's why not quantum gases, for example, such as Bose-Einstein condensates or polariton systems. So liquid helium is a wonderful substance. Below 2.17 Kelvin, helium-4 becomes a superfluid. Zero viscosity is not quite true. as you decrease the temperature, you have a knob of changing the viscosity in a system. Super interesting from a fluids perspective, the effective description. Also super interesting from a quantum field theory perspective, because it is an open effective field theory with a tunable parameter from open to closed. Now, it exhibits wonderful effects, the Fountain effect, the second sound, and quantized vortices. So rotation in these systems is quantized. They form like spaghetti, going like spaghetti through the system. They have determinant and n on the boundaries. And these are Armstrong-sized vortex lines in a three-dimensional system. And if you want to add a lot of rotation, or you easily end up in a regime that's called quantum turbulence. So instead of getting a nice ordered rotation, you can get this mess here as depicted in this system. So how can we make this helium-4 a suitable black hole simulator? Well, we have to overcome a series of problems. Well, the first thing is, which I already mentioned, why are you adding up in this mess? So if I have a single quantized vortex, which means that rotation is quantized, so a single vortex has a rotation of 10 to the minus 7 meters squared per second. And if I want to raise this rotation, then I can do this in integer steps. And it can be positive or negative depending on the orientation of your rotation. And what's happening if you try to crank up the quantization in the system, the energy scales with a quantization number or winding number squared. Hence, it's favorable for the system to decay into a stack of quantum vortices with winding number 1, rather than have a stack with a higher winding number. So energetically, the system simply doesn't want to be in large rotational states. And the other one, so this is the problem, they would spread out over the whole system. Now, which means is that in the vortex core, what Feynman predicted is if you have a vortex cluster that spreads out, around the vortex cluster, the fluid flow behaves irrotational. In the vortex cluster, you have a rotational flow. So hence, you want to keep, you can't prohibit really the decay of the vortex cluster, but you need to find a way to really keep it close together, ideally to form a single supersized quantum vortex. So our approach is reduce the density in the vortex core and adding a draining velocity component. So in other ways, we just repeat the same experiment, just in smaller scales and in a quantum fluid. This is what we've done. This is how the system looks like. And again, we are not, as everybody else would do in these systems, we are not putting this on a rotating table. Instead, we induce rotations externally. Now here we can't, of course, have this inlet flow, but instead of what we are doing is we add rotation magnetically. So let me talk you through the experiment. So here, this is the experimental setup. It's built out of glass for the reason that I just said. Instead of putting in a rotating table, you induce rotation magnetically. Hence, you can't use a conventional cryogenic system, which is made out of metal. So here, one is an outer glass door. This is an old style experiment, a double glass door system. There's the outer glass door here, where we have liquid nitrogen, and we pre-cool the system to 77 Kelvin. Inside this glass door, with the liquid nitrogen, there's an inner glass door that contains a superfluid helium-4, and we can reach temperatures, stable temperatures, down to 1.6 Kelvin. We have a pump line here because we use evaporative cooling, just as you cool your coffee cup, to cool this quantum liquid in the inner glass door. We have a science cell here that sits down here, and I made a magnification here. And what is new, or apparently very unique in this system, we have a top window that gives us access and a top view onto our cryogenic system. And this is what we do. We have these little magnets here, and outside my glass cylinder, there is a ring of magnets outside. They couple magnetically to this little, to the magnets inside my helium cell. This is mounted rigid to this propeller here. When that starts spinning, we created some flow straighteners, which are designed to guarantee us to get these irrotational vortex flows. To go through here, so these are 3D printed flow straighteners. And what we create is a circulation here, from the bottom to the top. And this allows us to reach high rotation without the need of a rotating table. So then, as I said, we have a window on the top, and we're looking at fluctuations. The way we did it, as you can see also in the setup, there were a checkerboard pattern. And what we used is, whenever you have waves on top of this, so for example, helium waves surrounding that vortex flow, they would distort this pattern. This is a very rough distortion. It's not that big for the experiments we're usually looking at. But here it gives a picture it shows you very well how you can see through the distortions of the pattern, which we are recording from the top, you can see the waves in the system. Perfect. Okay? So what is the accuracy you get with this kind of techniques? Well, you can resolve interface waves down to micrometer in space and time. So this is a wonderful thing about helium. When you look at it, you don't need to destroy it. These are non-destructive techniques, and hence you can map the system out in space and time and reconstruct the field propagation in a very efficient way. Okay? Right. So what do we get? So the first thing really was to understand, will you get a stationary draining vortex flow? There was a real question, because after all, this is a superfluid, and this is the stationary bust-up vortex flow has complicated boundary layer physics. So in other words, wasn't quite clear what exactly would be the outcome. Now it turns out, just as a normal fluid, you can spin up the fluid flow, and in particular, if you spin a little bit, you get a little dimple here in the center. You have to beat the surface tension in the system to open up the vortex flow. And if you spin harder, you can develop a hollow vortex core. And the question really is, where are the quantum vortices in this system? So in the quantum vortices, are they all, is this perhaps a single big quantum vortex, or are they close together? This is something we need to continue to investigate. It's maybe a question to follow up, because I'm running out of time. But what we did is we looked at the wave interaction, the waves interacting with the vortex flow, and from this you can probe the effective potential created by this vortex, macroscopic vortex flow. And what we noticed is that indeed you get an irrotational vortex flow outside, which is precisely what we need for the analogy. And then you can ask a question, how big is this quantum vortex if I divide it by the number of individual quantum vortices in the system? And what you will see is you get 10 to the 4 quantized vortices, and hence the largest quantum vortex flow in a superfluid realized. And the reason why here size really matters is because the higher the quantum vortex flow, the bigger the core becomes. And this core is macroscopic and can't be fit in a quantum gas or polariton system. So, and now I will end with 2 slides. So what more do you get by going through all the difficulties of setting up a superfluid vortex flow? And the first thing is, let's look at the ring down modes in the system. So before, in this big vortex flow, which is arguably much easier to set up, perhaps not as easy to control because an open system and water evaporates, so it's not as good for very accurate measures, but it's also not an ideal fluid, so you have a lot of dumping in the system. And what we've seen is we have a set of fundamental modes that we detected previously. So what happens if you redo this in a quantum system? And instead of just seeing the fundamental modes, you start to also probe the environment. And what you can see is precisely what Leonardo, I guess, talked about yesterday. Instead of only seeing the fundamental modes, you also see the overtones. And you see a plethora of overtones. And this is the first detection here of overtone modes in the system. And you can make theoretical predictions. The normal modes are not dumped. They can probe environmental effects. And what you can see is that the spectrum is changing, and we can precisely measure these spectral changes. So this is one thing that we did. So by going from a normal to a superfluid, a whole ton of new physics opens up, which you can then investigate. And that leaves me with the last thing. We know that if a wave-spinning black hole interaction, that the right kind of wave can extract some angular momentum. Now, if you repeat this in a superfluid, what's happening? The wave that stole some angular momentum, that impinges on your vortex flow, comes out, gets reflected back with a higher amplitude. Then it hits the boundary, which is the glass cylinder, and gets reflected back in. And it does so, and every time it goes back in, it gets amplified again. And so what you get instead of just superradiance, you can investigate superradiant bomb or instabilities. And this is one configuration, how it looks like. So what happens here is, in this case, the little wave is winning, and it really shakes this vortex flow. And what we're investigating at the moment is the nonlinear wave dynamics around this vortex flow. Okay? So that leads me with an end. This is my research group. The people with the heart here are not my favorites. Everyone is my favorite. But the people with the heart here are the ones who set up this fantastic experiment. And with this, I would like to end. Thank you very much.
Really wonderful experiment. An inspiring talk. Do we have questions? Yes.
Is it possible to hear me this time? Okay. My question concerns the very beginning, since everything here is about rotation. I think the work by Unruh that had this translation between fluids and GR, I think there was a requirement that the fluid is non-rotational. Does that matter for these experiments? Does one need to replace this transition between liquids and GR, or are we speaking about different kinds of rotations here?
Should I get a microphone, or should I just answer?
Reply with the mic.
You can use this one.
Okay.
Is it switched on or the other? I'm not sure. This is.
Okay, it's working. Yeah, so this is a very good question, which is why all the vorticity, so if you have a rotational vortex floor, it is rotational in the vortex core. The idea is to contain the vorticity in the core so that ideally you push out all the horizons outside the vortex core. And this is precisely the challenge. So, but in quantum systems, where vorticity wants to spread throughout the system, it would be rotational throughout. So exactly, this is the question, that you want to confine this centrally, because once you add rotation and vorticity to it, you don't have only a single parameter to describe your velocity profile. You have a three-dimensional velocity field, and then this analogy is less rigid. Having said that, it always turns out that these analog systems are extremely robust. So yes, it is more messy than the idealized calculations. The more we learned about this, we still try to comprehend and understand exactly how this works. And that one paper we're writing right now is to include vorticity and to understand how that plays a role in superradiance, for example.
Thank you. Very interesting talk. I wanted to ask about, so in the first example of Unruh, as far as I understand, the analogy goes that the kind of, you simulate what's happening on the slice of a black hole, just non-rotating black hole is just a slice, so 2 dimensions. But when we have a rotating black hole, you talk about the depth and effects on the depth, like on top and on the bottom. how does that relate? I was thinking that we can simulate only 2 dimensions, but then we can simulate 3 dimensions. How do those dimensions relate?
Yeah, it's a very good question, and I'm not mentioning it's a technical thing, but the question is about the effective metric. And the first thing what we need to realize is that this is an effective 2 + 1 dimensional metric space-time geometry, and here it is. And the first thing one also has to understand that all analog gravity metrics are conformally flat on the spatial slice. There's a theorem that has shown that you can't put Kerr onto such a geometry. You can't make Kerr conformally flat on the spatial slice. So, in fact, using just normal fluids or fluid flows like this, you could never mimic Kerr, even if you would find a way to work with sound waves and have a 3 + 1 dimensional effective metric. That's the first thing. Now, what turns out, what's important, one way to do it, to get full Kerr, would be using magnetohydrodynamic flows. And I have a paper on that with Matt Wisser. Now, putting this aside, you have a 2 + 1 dimensional metric. What is important here is that you can mimic anything that's going on the equatorial slice of the rotating black hole. And why is that good news? Because that's where you get all the interesting physics effects. So yes, it's a reduction of complexity, right? If you wanted to have a 3-dimensional black hole, you would need to have a point source, very hard to set up, very hard also to mimic, to extract the information you need. But this system contains every sort of a horizon that we're interested in to probe black hole ringing, superradiant bombs, Hawking radiation, name it, it's there. Light bending, it's all there.
All right, so maybe one last question and then we have to move on. I wanted to ask you, when you move from the classical to the quantum fluid, and you mentioned that there, instead of fundamental tone, you have also overtone, and sorry for my ignorance. So is this something where it's a purely quantum effect, or quantum fields provide you with a higher precision or stability to see something that would be present also in a classical fluid?
Classical?
Yes.
But in a classical fluid, you have a lot of damping. Sorry. So it's classical, but you need the property of the quantum fluid, an ideal fluid, otherwise you have too much damping in the system. So it's not, and this is a fine distinction, all of the things I presented are still, pretty much nice classical physics, but in order to probe them in this system and spectral stability, you don't want to have something that dumps out your modes. And we are also using this trick that because the modes are not damped, they can actually also test their environment. And spectral stability or the spectrum is changed, and it makes it easier to measure these overtones. Because black hole ring down modes or quasi-normal modes, they have a real part and an imaginary part. An imaginary part is a damping. So these are damped modes in the system. And the higher the overtone, the more the damping is. So you want to see something that dies very quickly, while there's something else in there that lives for longer. And so that's why a quantum fluid really is ideal to test this, and then to test nonlinear regimes of this. So it is a better fluid. It's an ideal fluid.
Great. Thank you. So let's thank the speaker once more.
Hi. Nice to see you. Nice to see you. Yeah. This is mine.
No. If you want to be on a video, you
take this.
Better keep on the platform, not go away. But I mean, we have sound recording. It's not a problem. But if you want to be seen, you have to be like that. So I think every talk is
3 minutes.
3 minutes. I don't know when.
We leave them now.
Shall we put 3 minutes warning? Clock warning? So all the speakers in this session, flash close to the podium forward.
1, 2.
Let's have a line. I suppose there are no questions.
Yeah, the posters are for questions, I think.
So, I will put a line. Please start whenever you're
Okay, this works? Or can you hear me? Oh, I need this. Great. Okay. I want to thank the organizers, of course, for having me, and also the Cost Action Bridge QG for funding parts of this research. Now, I want to use this time to briefly explain why somebody would want to do such a thing as field theory on non-commutative space-time. Well, we still don't have a full theory of quantum gravity, but historically, before we had GR, we had special relativity, which is an interesting theory in its own right. So one may hope that in the flat limit, quantum gravity could still leave some effects that we could potentially, hopefully, observe. And one such effect that's actually predicted by some models is non-commutativity of space-time. So the space-time coordinates having some kind of non-trivial commutation relation. Of course, we don't know what that relation may be. It could be many different things, and there are many different models. The one that I'm working with, Kappa-Minkowski, has this nice property of emitting an invariant length scale, which is something reasonable to expect of theory that comes from quantum gravity. Now, what do we do with this? We want to find some phenomenological implications. So we're trying to formulate field theory on this non-commutative space-time, and we are especially focused on the interplay between this quantum space-time and discrete symmetries, CPT. This is an effort that's been going on for quite some time. These are just a few of the most, I would say, important papers in the history, but there were, of course, many more. And what I will be presenting are some recent new results into the description of Dirac fields and a new perspective on how CPT could be described in Kappa-Poincare. So if you're interested, you can find me at the poster session. Thank you.
Hello everyone. Is there a pointer I can use maybe? Yes, okay. I'm Dario Capasso. I started okay. Sorry. I started my PhD in November in Florence, and actually the poster I'm going to present is an extract of the talk I gave last week in Genova for the ones of you who were there. And is based on a paper which came out before the start of my PhD, which is actually the thing I'm still working on from a different perspective. In particular, the main focus is on quantum time approaches, and in the framework of quantum time, we try to address the question of the title here. In particular, when I say quantum time, I refer to the Page and Butter's formalism, which is based on this assertion. If the universe is truly isolated, there is no place in the theory for an external time parameter, and whatever can be said about time evolution has to be extracted from an equation of this type. So a constraint equation which describes the state of a universe as a whole, while time has to be recovered as a physical system, via a physical system that is part of the system itself, of the universe itself. So starting from this operational description, assuming for economical purpose, for economy, that the system can be approximated via a finite-dimensional isolated system, we ask what can we extract from such a description in which the environment of a subsystem of the universe is engineered in a way that it describes a quantum reference frame. Here we focus on time, and basically the Page and Wutter's description allows to recover from quantum correlations between the environment and the system. It allows to recover the Schrödinger picture. And in particular, I will not go into details, but basically, this description in the finite dimensional regime allows to recover some phenomenology which in the context of gravitating quantum system allows for a correction of the Schrödinger equation that we call the time-dilated Schrödinger equation, creating some weird effect, I would say, that basically can be synthesized by the quantum time dilation arising from the interacting properties of the adopted clock are translated in effective interactions involving the other subsystem of the universe. For more detail, there is a QR code on the poster. I hope to see you later. Thank you, everyone.
Hi, I am Grzegorz Czelusta, and my poster is about simulating quantum gravity stage on quantum computers. Approaches like loop quantum gravity, spin-foam models, some other gravity emergent ideas use quantum many-body system to describe geometry. But the Hilbert space grows exponentially, so the classical numerical computational methods quite quick are intractable. So the quantum hardware is a natural way to overcome this bottleneck. And here we focus on spin networks, kinematical stage of loop quantum gravity. These are graphs with links labeled by SU2 holonomies, and in each node there is SU2 invariance imposed. And in this, and geometrically, each node corresponds to quantum of volume, and the structure of the graph corresponds to the way they are glued together. And here is the example where we have two 4-valent nodes connected by one internal link and 6 links at the boundary. And geometrically, it corresponds to two tetrahedra sharing a common face with 6 faces at boundary. And our pipeline is to map spin network stage to quantum circuits. So first we map it to the tensor network. Each node corresponds to the rank 5 tensor, where 4 indices M1, 2, 3, 4 corresponds to the links of the node, and internal and additional index k corresponds to the internal degrees of freedom of this node. And holonomies at the links here become Wigner matrices of SU2 elements. And then we map it to the quantum circuit, where each node become a quantum gate. This gate is in general non-unitary, so we need projective measurements at the end. And each Wigner matrix become a single qubit gate. And we have explicit form of these gates in terms of simple elementary gates. Having in hand this quantum circuit, we can prepare a bulk boundary map, that is map from the bulk degrees of freedom to the boundary degrees of freedom. And in this setting, there is a known formula for entropy of bulk versus entropy of boundary for this kind of spin networks. So we can check our attempt. We simulated a spin network and computed the mutual information between parts of boundary. We see that the blue and orange distributions are shifted by 2 with agreement of this formula. But what more, we see that the shape of distribution for boundary comes from random bulk is different than random bandari generate directly. So it raises a question, what does it mean to have random geometry in this case? So to sum up, this is not only the method to use on future quantum computers, but this also, it can give us insight into quantum gravity state from the point of view of quantum computations. Thank you.
Hi everyone, I'm Sean. I'm a PhD student at the Gravity Laboratory at the University of Nottingham. So Silke was talking earlier about analog gravity, and the work of myself and my collaborators is to use the methodology of analog gravity to look at cosmology. So first I'll talk a bit about the experiment that we have, and then I'll talk about how that relates to cosmology. So the system itself is a fairly simple fluid mechanical tabletop setup. So we have two fluids that we fill a vessel with, and they separate out to form an interface between those two fluids. Now this vessel with the two fluids we mount to a bespoke shaking platform which provides a periodic forcing. So through a process known as parametric resonance, this excites one particular large length scale wave mode. And then through nonlinear interactions, the energy passes from this one wave mode to wave modes at larger wave numbers. And so we see in real time the build-up of what's called a direct energy cascade, which is characterized by a power law scaling behavior in the power spectral density. So this is the process that we look at, and it is a general far from equilibrium process, and it also appears in the context of cosmology. So we look at the theory of cosmological preheating. So right after inflation, at the beginning of the universe, so inflation is a period of time in which the universe rapidly expanded, leaving the universe empty and cold. Now the universe had to heat up again, we had to produce matter particles, and they had to thermalize. Now the process with which that happened is there was a quantum field known as the inflaton, which drove the expansion of the universe, and this comes to oscillate around its potential minima. So in our analogy, this oscillation is provided by the shaking platform, and we consider a coupled scalar field, which in our case is the interface between the two fluids, and in the case of cosmology is some scalar field. Through the exact same process, energy is transferred to the scalar field, or the interface in our case, which produces a narrowband resonance, a rapid expansion of an excitation. And through the same process, these nonlinearities, energy is transferred, the system redistributes until eventually a steady state is reached. So through our experiment, we've been able to learn both about the fluid dynamics of the system and also about the cosmology to which it's analogous. So if you'd like to learn more about this, I'd encourage you to come find me, come find my colleague Sylvia, who's here also, and have a chat with us about this project. Thank you.
The next speaker is Lewis. So I invite him to come.
Thanks, everyone. Hi, I'm Dominic. I'm from RMIT, one of Nick's students, and this is some work that we did in collaboration with some people from Macquarie and also Achim from Waterloo. It's talking about Shannon wavelets and holographic-like lattices in quantum field theory. So, as some people here may know, for the last few years, people have been talking about how ultraviolet cutoffs and band limitations can give us an isomorphism between non-local lattice theories and continuous quantum field theories in spacetime. So an ultraviolet cutoff to a QFT, it permits an equivalent lattice model of coupled harmonic oscillators, with the only caveat being that these lattice models are non-local and have polynomially decaying coupling strengths. But in terms of the actual relationship between the lattice model and its continuous counterpart, well, they're the same picture. They give exactly the same physics. However, they have an ultraviolet cutoff. This is another downside to these theories. And the question became, what happens if we want a field theory that that doesn't have an ultraviolet cutoff? What if we just want to try and extend this equivalence to something without such a disadvantage? So, using a Shannon wavelet basis, we can do sampling theory on fields without a cutoff. And this boils down to taking the momentum space of a field and separating it into discrete layers where each layer acts as its own band-limited field with a cutoff. So we just take momentum space and split it up into as many different kind of cutoff fields as we like, and each of these have their own lattice models, but the whole thing stacked together are their own theory. So we can layer these lattices on top of each other and place them on top of each other like this, and observe that the length scale of each layer seems to scale hyperbolically. In fact, if you start with this d-dimensional continuous QFT and end up with this d+1 dimensional discrete one, just by taking this Shannon decomposition of our momentum space, we get something that looks like it's got hyperbolic-like geometry. So, a lot of this comes down to how do we explicitly determine what this geometry is and push how far this hyperbolic-like geometry and almost holographic-like principle to our wavelet-based decomposition. Well, if you want to find out how deep this rabbit hole goes, please come to my poster.
Okay, in this talk I would try to argue that the best framework of quantum mechanics or formulation of quantum mechanics for quantum gravity is the modified de Broglie-Bohm formulation, where modification is essentially to replace the equations of motions of de Broglie-Bohm, which are first order in time, by the effective action equations of motion, which are second or higher order in time, and this has its advantages. So in this way, one can improve the de Broglie-Bohm formulation, but also that's convenient for quantum gravity. So the advantages of the de Broglie-Bohm formulation is that their particle trajectories always exist, no wave function collapse. So no need for an observer, and here the de Broglie wave function is really the wave function of the universe. And the usual wave function is obtained by what is called conditional wave function. So you, in the wave function of the universe, you have to replace the coordinates of the rest by their solutions. So this wave function then has a possibility of the dynamical collapse and can display certain features we need from a wave function. Now, what are the problems? Is the violation of the Heisenberg uncertainty relations for stationary bound states. This can be, the reason for this is because the momentum and the coordinate are not independent variables in the usual de Broglie-Bohm formulation. Then there is no clear relation between the classical and the quantum trajectories. Essentially, there are no semi-classical trajectories, so it's difficult to find them. And the third problem is the quantum field theory formulation is difficult to obtain in the there. So so the way out of this is simply to replace the check here. Where is it? Is to replace the usual de Broglie-Bohm equation with the effective action. And here the any wave function can be written as the real part times the phase. And while the effective action is what is essentially defined by these relations, which is Legendre transform of the path integral, but with the source. And this is this quantum field theory definition of the effective action. And in this way, one can then one can actually easily generalize to the quantum field theory case simply by replacing the using the standard quantum field theory action. It has this property of the semi-classicality. You can always get the solution, which is the classical plus the quantum corrections. And then you can show that P and Q are now dynamically independent, so Heisenberg relations are not violated. Particle trajectories can be easily defined as the maximum of the psi square. And the only problem that the quantum field theory effective action is only defined for the vacuum state. And then quantum gravity helps you for this because you can define what is called quantum gravity effective action, which can be constructed by using a path integral for a manifold, which is like this is the M0 is like a Hartle-Hawking manifold times a cylinder. Okay. So the workable example is given by the piecewise flat quantum gravity theory. See book by Miku, Chen, Wojnowicz, World Scientific 2023.
Okay. Hi, my name is Sebastian. I'm a postdoc at the Okinawa Institute of Science and Technology in Japan. And my poster is about a piece of work conducted in collaboration with Daniel Turner and Rama Vadapalli from Macquarie University in Sydney. And this has been published in Physical Review D earlier this year. There we go. So in this work, we investigate what is known as gravitational birefringence. Sometimes it is also called the gravitational spin-Hall effect of light. And if you have taken an introductory course in general relativity, then you will have learned that photons follow geodesics. And this is true in the geometric optics approximation, but beyond geometric optics, we actually know that the polarization will influence the trajectory of photons. And in general, that trajectory will deviate from that of a null geodesic. And this is what is described by the polarized ray equation that you see here. So you can see sigma, the polarization enters, omega is the frequency, the curvature enters via the Riemann tensor. And in our paper, we use the Newman-Penrose formalism to evaluate the trajectory of these polarization-corrected photons. And also, we do this using what is known as the Fermi-Walker transport law. So this law ensures that all of the curvature that you see is really genuine curvature due to the mass and energy density rather than to some curvature or spin that is associated with the frame that you're working in. And analytically, this is actually kind of tricky because in order to construct the tetrad, you need to know what those corrections are. So the way to go around that is to use a perturbative approach where the lowest order is just the geodesic, and then you add your polarization-induced corrections to your trajectory. And numerically, what you can do is you can actually incorporate the Fermi-Walker transport law into your system of equations, and that'll make sure that this is satisfied at every step of your iteration. Now, ultimately, the goal, of course, is to make contact with experiments. So we looked at two specific scenarios that are relevant for astrophysical observations, namely the deflection of light by a massive gravitating body and the emission of light by a massive gravitating body. And what you see in the top here is the black line, which is the numerical solution, and the colored lines are different steps in the iterative solution of the analytic procedure. And you can see that for the deflection scenario, with only the first 4 terms, so the 3 lowest iterations, you already get extremely good agreement between the numerical and the analytical solution. And in fact, for the emission scenario, you only need 2 terms, so 1 iteration to get very good agreement. And there's a bunch of other things that we did in the paper, but due to the time, I will stop here. And if you're interested in this, then please come see me in the poster session.
Test. Hi. Test. Hi. I want to start with a claim. The claim is that any asymmetry in time is thermodynamic in origin. You might already accept this. You might disagree for specific reasons. If you have never thought about this, take it for the sake of a presentation. So what I'm doing in my poster is that I try to tease apart what is in quantum mechanics given by nature and what is inference or mere knowledge. And then I interpret quantum mechanics as involving some kind of retrocausal influence. And then we can intuitively understand 2 things. And the first point is quite a lot more interesting than the second one. So that's what I'm going to try to convey to you here in a very short time. It's about how is it that knowing all there is to know about the total system of an entangled state, one knows as little as possible, about the individual subsystems. Why is it that when we trace out Bob's subsystem, Alice's subsystem is represented by a maximally mixed state? So first, why is it that I think that retrocausal influence is not so problematic? The reason is that in a quantum mechanics experiment, your system is completely isolated from the environment. Only the environment has a direction of time. Only the environment is thermodynamic. So in the confines of a quantum mechanics experiment, whatever happens in there is supposed to come out time symmetric. And so the kind of picture I want you to have in mind is that in a Bell experiment, the 2 systems, they form some kind of space-time worm, and influence is mediated between Alice's measurement and Bob's measurement bidirectionally in some kind of either retrocausal or atemporal way. And a metaphorical picture that I think is useful. Imagine 2 people pulling a chain and they feel each other's pull. And in the Bell experiment, Alice's probability, it depends on all the relevant variables of the experiment. It depends on Bob's choice of measurement, Bob's outcome, Alice's choice of measurement. And it depends on these relevant variables together. If Alice is completely ignorant about any of these variables, she will assign a uniform probability distribution to her outcome. And this is the reason why we represent Alice's state with a maximum mixed state. So tracing out Bob's subsystem, it results in a probability distribution of Alice's outcome of 1/2, a uniform probability distribution over the 2 outcomes. The same happens if Alice is ignorant about any of Bob's variables on Bob's side of the experiment. And I think that this correspondence is deep, and this lends credence to interpreting quantum mechanics as involving some kind of retrocausal influence. If you're interested in hearing more about this, come to my posters. If you're the author of this paper, I think I know a small philosophical community that wants to cite you, so come talk to me. And thank you for listening.
So we're done with the session. I would like to thank all the speakers because they were told that this was the way they were presenting the flash talk just 2 days ago. So they were very good at preparing and presenting. Thank you.
Take your seats, please. We're going to open up the next session.
What am I doing
The
wrong?
camera is set up only for this part. If you don't want to show the camera, it's okay.
Okay, because I walk. I don't think about it and I keep walking when I speak. So like, what is the...
Reference frames. Yeah, you need to stay on in the photo.
Okay.
You're really photogenic. Just do it.
No, it's just that I walk when I speak.
Okay, we'll walk here.
Okay. Okay, great. So thanks a lot, Rob, for the introduction, and thanks a lot to you all for being here. And it's a pleasure to be back at this conference. So also thanks to the organizers for inviting me to give this talk. I'm very happy to be at RQI and in Naples. So I was asked to talk about quantum reference frames. So also thanks to everybody in the Costa action for voting the topic. So what I would like to focus on, since this is an audience where many people are already familiar with quantum reference frames and you have encountered them in different ways, is to say a few words about how quantum reference frames can contribute to generalizing the Einstein equivalence principle to situations in which either matter or gravity is quantum. And let me start from setting the stage for what we mean by equivalence principle. Everybody knows that, but since I will need some specific features that motivate its extension, then it's better to have a common language. So let me start from some features of general relativity that are quoted in this article here. So basically, word lengths of massive test bodies are time-like geodesics. Photons propagate along null geodesics, and there is a link between the proper time registered by an ideal clock and the metric. These are all statements that do not depend on Einstein's field equations, but they depend on the equivalence principle. And to put it in the words of Misner, Thorne, and Wheeler, the principle of equivalence has great power. With it, one can generalize all the special relativistic laws of physics to curved spacetime, and the curvature need not be small. So basically, this means that the equivalence principle gives us a recipe to be locally, at some point in spacetime, we write the laws of general relativity, and then we have a rule to transform these special relativistic laws into general relativistic laws. So it is not just at the heart of the conceptual foundations of general relativity, but it is also a fundamental tool to construct the theory. So always according to Misner, Thorne, and Wheeler, the statement of the Einstein equivalence principle is that in any and every local inertial frame, anywhere and any time in the universe, all the non-gravitational laws of physics must take on their familiar non-relativistic form. So basically, the metric becomes locally Minkowskian at any point that you can describe in spacetime. And there is an equivalent way of stating the principle that is more amenable to experiments. So basically, you can divide the principles in three aspects: the weak equivalence principle, that is the universality of free fall; the local Lorentz invariance, that is that the outcome of any local non-gravitational experiment is independent of the velocity of the freely falling reference frame in which it is performed; and local position invariance, that states that the outcome of any local non-gravitational experiment is independent of where in the universe it is performed. These three aspects are not fully independent one from the other, and some of you may be familiar with the Schiff conjecture, but anyway, this is a useful classification in order to perform a test of the equivalence principle. So now, how do we test it? So a typical test of the equivalence principle uses clocks. So let us imagine the following situation. We have two clocks in the gravitational field of the Earth at two different heights. And we know that according to gravitational time dilation, a clock that is lower in the gravitational field ticks more slowly than a clock that is higher in the gravitational field.
And there are experiments that started with the experiments in the group of David Wineland since 2010, where they basically measured this effect with atomic clocks. And here, initially, what this experiment did was to put a clock on an optical table, measure the rate of this clock, then literally lift the optical table by 30 centimeters, and see that the rate at which this clock ticks is different. So now these experiments are much better. They can test gravitational time dilation at the level of the millimeter. So this is an amazing result. And so how does a test of the weak equivalent of the Einstein equivalence principle goes? And in particular, let's focus on local position invariance, because this is what I will talk about later, that uses the universality of gravitational redshift to be tested. So let's take these two clocks in the gravitational field of the Earth, and let us assume that we are in a weak gravitational field, and the gravitational field is static. So these are all simplifying assumptions, but of course they're not necessary to state the principle. So now, clock 2 sends a photon to clock 1, and the photon is emitted with some frequency, and it is received at a different frequency because of gravitational time dilation. So now, and when you perform this test, you always assume that the other two aspects are valid, because you test them independently. So I can define a freely falling frame that is momentarily at rest with one of the two clocks, in which the metric is just takes this form. And then, if I have a violation of local position invariance, this means that what I wrote here is not valid anymore. So, what is usually done is to assume that there is a time dependence of the proper time in the freely falling frame co-moving with the clock that depends on the position of this clock, and in particular through the gravitational field. So then you can transform back to the laboratory frame. Oops. No. Okay, you can transform back to the laboratory frame, and you will obtain this equation, this line element. Okay. And then if you calculate the emission and the reception frequency, then what you obtain these laws here, where you see basically the violation of the principle is encoded in this tau to the -1 of emission and reception. And now if I take that, I can define this Z quantity that is basically the difference between the reception and the emission frequency renormalized. And if you expand this perturbatively, you end up with this expression, where then you can further, Taylor expand, for instance, the tau of phi reception from basically using this as the center of your expansion. And in the end, you can simplify the Z quantity like that, where alpha is the violation parameter. Okay. So how do I generalize, and what are the conditions in which I need to generalize the equivalence principle? So there are, first of all, a disclaimer. There are many people that studied quantum generalizations of the equivalence principle before, so this is definitely not a new topic. And there are many papers that define that, and they define it in different ways. So this is just one possible way of defining a generalization, an extension. Some people say it's violated, and there are even more than what I just drew here. Okay, so a first very easy way to understand why the principle should be generalized is to consider a quantum particle that is in the gravitational field. That is in the gravitational field of the Earth, and we write the Schrödinger equation for it. Now, if you calculate the dynamics of this quantum particle, so you see how the particle evolves in time, then you find that the Green function of this particle, so the time evolution, depends explicitly on the mass of this particle. And this is something that classically is not true, so because of the universality of free fall. So you have two options here. you either say that you have to, the equivalence principle is violated, or that you should modify it. And since the gravity here is the same theory, so gravity doesn't change, so my personal inclination would be towards an extension of the equivalence principle in this case. And there are other ways in which we are not in the assumptions of the equivalence principle as stated in general relativity. For instance, the trajectories of the particles that are used to test the equivalence principle may be replaced by quantum states, so there is no notion of trajectory, and we need the trajectory of this particle for to state the equivalence principle. Then the reference frames attached to the particles or to the clocks in the experiment of universality of gravitational redshift that I told you about become quantum reference frames, and I will be clearer on that in the following. When such particles or clocks are in a quantum superposition state, the internal energies of the particles become quantum operator, and gravity is quantum. And I will not talk about the last point here, just very briefly. So, what are quantum reference frames? Just they have been mentioned during the conference, but let me just tell you the very, very basic example that just to set the ideas. So basically, quantum reference frames is naively the idea that you associate a reference frame to a quantum system that is in a quantum superposition. So the naive question one wants to answer is what happens if I have an atom in a quantum superposition and I want to look at the world from the perspective of this atom. Clearly, this is a super naive question and things are more complicated than that. But what it turns out is that, for instance, imagine that I have I start from some reference frame A that I symbolically write as if it was in the origin, and then I have another quantum particle B that is in a quantum superposition of two positions. Then I want to take the perspective of B, and what I can do, I can come up with a unitary transformation, okay, that is a quantum reference frame transformation that centers the origin on B, and then I will see A in a quantum superposition of being in minus x1 and minus x2, where B now is at the origin. So now this is unitary, so you can go back and forth between the two frames as you like. Okay, so this is basically everything that I need for the following. So now let us move to the statement of the quantum Einstein equivalence principle, and basically the core of the generalization is the introduction of the notion of a quantum locally inertial frame instead of the locally inertial frame that we had before. And so what is a quantum locally inertial frame? So this is a quantum reference frame, first of all, and this can be either a quantum reference frame where we have, for instance, an atom in an interferometer that is in a quantum superposition of positions and in a classical gravitational field, and then we want to take a quantum reference frame transformation such that the metric is locally Minkowskian at the position of this particle, of the atom in the interferometer. And you need a quantum reference frame transformation to do that, because if I have a quantum superposition of positions, there is no single coordinate transformation that can make the metric Minkowskian at these 2 points. But it can be also something wilder, and this is something which we have worked with Czeslaw. And so, for instance, we can have a quantum superposition of gravitational fields and a particle that is entangled, say, with this gravitational field, and you want to take a superposition, again, of coordinate transformations such that the metric is locally Minkowskian at the position of this particle here. And so, before I move on, let me just say a couple of words on what do we mean when we say quantum superposition of gravitational fields or of space-time. So in general, this is not a well-defined concept in full generality. However, you can make sense of it in some specific situation. For instance, in situations that have been addressed in this conference on Tuesday, where you have a massive particle in a quantum superposition state, and that sources a gravitational field. You can write this gravitational field using linearized quantum gravity, and then basically if the particle is in a quantum superposition of localized states here and there, then we have effectively a quantum superposition of spacetimes. And then you can notice, okay, but that actually gives me some intuitive picture of what a quantum superposition of spacetime is. And so I can extrapolate some principles according to which I will still have a quantum superposition of spacetimes without assuming that this gravitational field is weak. And so you can write something like that, a quantum superposition of manifolds, which has some, which respects some criteria. In particular, that you associate orthogonal quantum states to macroscopically distinguishable gravitational fields, that each well-defined gravitational field is described by general relativity, so in each one of these manifolds I can use GR, and that the quantum superposition principle holds for such gravitational fields. So there we do not know like how to physically identify really this regime in the most general situation, but again, we have situations that are physical, and we can say that this corresponds to the requirements that we have here on the right-hand side. Okay, this is all I wanted to say about that. So let me move now to the test of the Einstein equivalence principle in quantum reference frames. And this is work that I did with Carlo Cepollaro, who was at the time a master's student. And he's now in Vienna doing his PhD. So basically what we did was to rephrase the three aspects of the Einstein equivalence principle. And you see we added just some quantum here and there. So in particular, I will focus on showing you how the quantum local position invariance, a quantum local position invariance test would look like. And basically, you see that here we have that the outcome of any local non-gravitational experiment is independent of the position of the quantum reference frame in which it is performed. So in the following, we will assume the other two aspects, as is done customarily in tests of the Einstein equivalence principle. So for that, we need quantum clocks. What is a quantum clock? So a quantum clock is a two-level system that has some internal degrees of freedom that basically record proper time in it, and then some external degrees of freedom that is the path that the clock takes inside the interferometer. And it was shown by Magdalena, Fabio, Igor, and Czaslaw in 2011 that if you put them in an interferometer and then you measure, you perform a measurement at the end of the interferometer, there is a very distinctive signature of the fact that the proper time elapses differently in each path, that is a reduction of visibility in the interferometer fringes. And this is something that we will need in the following. So now let us consider one of these a situation in which we have a clock in the reference frame of the laboratory of the Earth. And then we have another clock in a quantum superposition of position. So like in an atom interferometer, for instance, the geometry of the interferometer is not particularly relevant for us. So you can pick your favorite interferometer for this. And we just send the clock in interferometer and we let it record proper time according to its path. So now imagine that clock 2 sends a photon, so emits a photon at some frequency and it sends it to clock 1. So we do not know anymore at this point which frequency clock 1 will receive, because we have a quantum superposition of paths, so we will have a quantum superposition of gravitational time dilations. So we need to define a freely falling frame momentarily at rest with the clock according to tests of universality of gravitational redshift. Here we do not have a single frame, so what we need is a quantum reference frame, so a quantum local inertial frame, basically. And you can show that what happens is that this Z quantity that quantifies the violation of the Einstein equivalence principle basically becomes an operator. And an operator in this case for the UGR, so for the test of local position invariance, in such a way that the alpha parameter of violation becomes an operator on, specifically on the position degrees of freedom of this clock in the gravitational field, while the rest stays the same. And then we can make a test. So you can send two clocks in the gravitational field. So the test with entangled clocks are needed just because you want to go to the quantum reference frame of one clock and look at the other, but one could also imagine to do it with one clock. And basically, you just perform an interferometric experiment, and you record the probabilities of the outcome at the end of this interferometer. So what you do is you trace out the clock degrees of freedom, and you recombine the paths at the beam splitter, at the second beam splitter, to basically forget the which way information of this clock, so basically to observe interference. So now, if the universality of gravitational redshift is violated, you see that you have a modified expression for the scalar product between the state of the clock in the second path and the clock in the first path. That is, this would be the one when there is no violation, and then you see that you have the violation operator here, alpha, that is evaluated along the trajectory of the clock in the interferometer. So this is the thing that should be zero if we have a universality of gravitational redshift. And remember that the scalar product between the clock in the two states was the quantity that tells us the reduction of visibility in the interferometer. So in the end, what you get is that this quantity appears in the probability at the end of the interferometric setting. So this is something that can be tested in atom interferometers. So basically, a violation of this definition of the Einstein equivalence principle appears in the probabilities at the end of an atom interferometer with quantum clocks. Okay, so one more comment on that is that this generalization of the Einstein equivalence principle is also related to the possibility of basically of having a spontaneous state reduction that was introduced by Roger Penrose in 1994. So in particular, Roger Penrose, when he argues in favor of his semi-classical gravity, of the fact that gravity should remain classical, one of the arguments that he uses is the incompatibility between the principle of linear superposition on the one hand and the Einstein equivalence principle and general covariance on the other hand. So what he does is he prepares a source of gravity in a quantum superposition state, lets it evolve, and then he notices that there is no single coordinate transformation that can make the metric locally Minkowski because we have a mass in a quantum superposition. Then he says, okay, but what about I take a weak approximation for the gravitational field, so I still have a Minkowski background to refer to. And then he says, well, but actually, even in this situation, I would have different Killing vectors that are conservation, tell us that we have conservation laws. And so in the end, the global state has an uncertainty in the energy of the gravitational field, and having an uncertainty in the energy leads to an unstable configuration. So there will be some decay time, basically some time over which one of these two amplitudes will die out. And he even identifies what this time, basically over which you would have the state reduces to just one single configuration of the gravitational field. And this would be the h bar divided by the difference in gravitational energy between the two configurations. So, but what I've shown you now is that the starting point that Roger Penrose uses, that is that we have basically the mass in a quantum superposition, there is no single coordinate transformation that makes the metric locally Minkowski, can be overcome if you generalize the coordinate transformation to a quantum superposition of coordinate transformations that quantum reference frames allow you to do. And so using quantum reference frames can overcome the objection that Roger Penrose has about the incompatibility of the Einstein equivalence principle and quantum theory, and so you can reconcile these two principles by simply extending the range of validity of the Einstein equivalence principle. Okay, so this is everything I wanted to tell you. And so the summary of my talk is that when gravity is quantum or it is tested with quantum systems, we go beyond the usual definition of the equivalence principle. And that we can use, in these situations, quantum reference frames to extend the definition of the Einstein equivalence principle to the quantum regime. And the core of this extension is the introduction of the notion of a quantum local inertial frame. And in classical gravity, the extended equivalence principle could be tested in atom interferometry, and I showed you an example of part of what this test would imply, that is a generalized test of the universality of gravitational redshift. And if, so for people among you who are interested in or know about Page and Wouters, so formally, what we have to do to write down this test, since we want to look at the perspective of basically of the clock from the laboratory frame to the frame of the atom in the interferometer, basically we use a framework that looks a little bit like Page and Wouters, but we also add the external degrees of freedom of the clock. And you can formulate, so basically we have some neutral structure from which we start, and then from which we can reduce to the single perspectives of a specific clock. And now what happens is that if we have a violation, we can model this violation in a specific frame, and by compatibility, we find also how the modification should appear at the level of the neutral structure that is above, like say, at the level of the constraint of Page and Wouters. And if you do that, and then you use a reduction procedure as you would do in either Page and Wouters or the perspective neutral approach of quantum reference frames, then you find that you cannot define a history state anymore. So it is really like the possibility of defining the perspective of that quantum reference frame that becomes non-valid if the Einstein equivalence principle is violated. So this would also be indirectly a test of the validity of the quantum reference frame perspective if we perform such a test. And with this, I would like to thank you for your attention.
Okay, thanks, Federico. That's nicely on time, a bit early, so we have time for questions, and I think you're going to take the mic, the mics around. So I think I saw Cisco first at the back, but I'll keep track. So,
okay. Yeah.
This thing on.
Is he supposed to?
There.
Thank you very much for that nice talk. I was just curious, this extension of the equivalence, the weak equivalence principle to include transformations with superpositions involved of coordinate transformations, does this remove the entire motivation for Penrose's suggestion about?
Sorry, what is the entire motivation? The generalization was motivated by Penrose, you mean?
Yeah, to remove the incompatibility between the equivalence principle and these superpositions of geometries. So once you've resolved that, is there no longer a motivation for Penrose's instability? Or is there some way to reconcile?
So,
do they still come together in
so
some way?
I think that if you accept, so at least all the motivations that I know that Penrose gave, once you accept that all the quantities that you define in general relativity or in quantum field theory, for instance, another motivation is that the vacuum state of the field is not the same for the two configurations. So once you accept the quantum reference frame perspective, then you also accept that also these quantities can be defined in a quantum superposition. And so at least all the motivations that I know can be rephrased in terms of this extension. And so it's, yeah,
Okay. Thank you.
You can overcome them.
Okay, and there was another question right here. Yep.
Okay.
I'm convinced of the importance of quantum reference frames that they are needed. However, in your motivation, there is something which left me a bit perplexed. If we go on top of the Pisa Tower, you go, I stay down, and you drop 2 balls, one will arrive earlier. Now you don't give away the equivalence principle because of viscosity. So you just say that the gravity is not the full thing. Now, if you put a Schrödinger equation, even a free particle, the behavior will be depending on the mass because the spreading of the wave packet. So I'm not really convinced. The rest is okay, but that particular example left me slightly perplexed.
Okay, but so this is more because of the generalization of the weak equivalence principle, what you're asking. Sorry, can you hear me now? Okay. So what you're asking is more about the generalization of the weak equivalence principle. Okay, so the thing is that experimentalists are interested in performing tests of the weak equivalence principle, for instance in atom interferometry, where they have a superposition of paths. And then if you really apply the usual rules that you would take for the Einstein equivalent, for the weak equivalence principle, then you don't have the same formulation. So you have to tell them what other thing they have to test in that case. And then you can even generalize. Now there are the experiments in Markasevich's group at Stanford where he can put an atom in a quantum superposition at 2 different small g's. So where, say, the Taylor expansion of the 1/r potential here and here gives you a different small g factor. And in that case, this is just like an even more general extension because you cannot have, you don't have the same G here and here. And so in this case, you really need a quantum generalization.
Okay, are there other questions? Oh, over here? Yeah, Daniel? Oh, wait for you.
Can you hear me? Yeah, very nice. So in terms of testing this, even in the classical test of the equivalence principle, I often ask this question, like, what is the model where the equivalence principle is violated that you're checking against? And I'm wondering if you have an answer in this quantum version. So what I mean is, right, like, is there a detailed model where there is a violation of this thing? Maybe the Penrose model is an example.
Yeah, the Penrose model would be an example in which the Einstein equivalence principle is violated, but what you usually do is what you want to test the validity, so you take by hand basically the fact that one of the 3 elements of the equivalence principle is valid, you introduce a violation parameter, so it's not a theory that you're violating, but you put by hand a violation, and then you test the bounds on the violation parameter or operator in this case. So you're not contrasting 2 theories in this case. You want to test a principle that for some reason should be violated.
Okay, let's thank Flaminia again. So we'll wait for the next speaker to get set up.
Yeah, this is mine, so
it's both okay. I can give it back to you later.
Yeah, okay. So yeah, just don't forget it.
Thank you.
Oh, sorry.
Oh yeah.
I don't want to be recorded.
Oh. So I will use this. I tested yesterday, it works.
You'd rather speak directly into that?
Yeah.
Okay.
Yes.
Do you want to use this? Do you want to connect this one too? So
yes.
Here, so you can swap pages with that.
I was
Okay.
thinking if it could be raised.
It's fine. I tested yesterday. Yes.
Okay.
I'm good.
And you don't need this one?
And I will speak.
Yeah, on the screen. There we go. So are you ready to go?
Let me test whether it moves. Yes.
So Barbara will take my place for the questions. Okay, good.
Okay, so our next speaker is Linqing Chen, who's going to tell us about 3 aspects of relational approaches toward background-independent quantum space-times.
Thank you, Rob. So first of all, I would like to thank the organizer giving me this valuable chance to speak in this wonderful conference. Last year, when I visited the University of Napoli the first time, it was the best hospitality I have ever seen in any cities. So I'm really happy to be back. So this talk is about 3 aspects of relational approaches towards a quantum space-time. I will discuss 3 fundamental aspects in collaborations with this a group of very wonderful collaborators. And the topic covers 3 projects, which ranges from quantum information field theory and gravity. So I hope that, I know despite that you are very hungry right now, there is some part of the talk it will be particularly interesting for you. So I will start from the first aspect, the notion of events and localization without background space-time. This is in collaboration with Villassini, who is here, and Liu Han and Renato, based on this paper. So in general relativity and in quantum physics, the notion of events, localization, and causality are different. So in general relativity, events are the element of space-time manifold independent of agent, and it's always tied with the geometry. However, in quantum physics, events are defined operationally through measurements and intervention, depending on the observer or the agents. So to combine the different notions, the notion must be bridged in order to have a consistent description of quantum experiments in the relativistic regime and to understand quantum information processing in the whole space-time. Moreover, the need for reconciliation is even more pressing and challenging in the regime of quantum gravity when we don't have a classical space-time background. So our approach starts as following. Initially, we do not assume background space-time, specific regime, or specific theory. By specific theory, what I mean is that it could possibly be quantum physics or beyond quantum physics, such as, for instance, more general probability theory, etc. And we want to start from basic operational considerations. What information and the degrees of freedom can, in principle, be accessed and acted upon relative to what kind of structure we need to define to make sense of the events and the localization. And this is an important point I learned from Villassini, that in quantum information field, to verify causal structure, it is really not enough to passively observe. One need to do active intervention to verify the causal structure. And this active intervention could be something one can do in the lab, but can be also something theoretical. For instance, the moon's orbit influences our tide. In the theory, we must have this element of freedom such that the imaginary intervention could be carried out in order to check the causal influence. So therefore, based on these considerations, we take the following set of minimum assumptions. So this is a bit abstract, but soon you will see how it plays a role in a concrete example. So it is possible to distinguish 2 types of degree of freedom. The target is the system of our study, and the reference degree of freedom. We consider the reference degree of freedom as the function of we are studying the conditioned operation on the reference. For instance, I turn light on at 5 p.m. This can be written as a conditioned operation based on such reference. Important to note that this is a different notion of the quantum reference frame that recently have been studied. So, for instance, a spin can serve as a quantum reference frame, but in this context, a spin as a controlled degree of freedom can serve as a controlled degree of freedom for the C0 gate. And so the next point of the assumption is it is possible to measure this degree of freedom and observe distinguishable outcomes. Then we want to introduce the structure that the notion of events need to be defined relative on. We call it the generalized lab. This lab can be the physical laboratory or can be theoretical lab. For instance, I'm studying some star collisions. And so a generalized lab is specified by 3 elements. First, the reference degree of freedom along with the measurements, and whose physical outcome is distinguishable and mathematically decompose the reference degree of freedom into subspaces. The second is the target, and the third is a set of operations we are considering. And this set of operations, in general, we can always written in a form that conditioned on the reference to act on the target. So then, within this definition of generalized lab, each operation in the set of possible interventions we are considering is said to be an event relative to this lab. So note that specifying such a structure, it codes the choice of the level of the detail of the description of the theory, reference, your choice of reference and target, and the set of operations. Also, the standard notion of events, for instance, particle scattering, collision of black holes, operations, this can be all recovered in this notion. And so usually expressed as operations controlled on the usually implicit or explicit space-time reference degree of freedom. Okay, so now let us look at a concrete example. Based on this definition and this minimum structure, we can already resolve some debate. So what we want to look at is quantum switch, which is an abstract process or quantum supermap with indefinite causal order. Depends on the control. By superposing the process, one encountered the operation A or B, which happens first, is indefinite. And there has been, this is a very active research field for the last more than a decade. There are quite a lot of physical realizations. One is this optical quantum switch experiment that can really carry out in the lab. The other one, that is a beautiful paper by those authors about gravitational quantum switch, which is a thought experiment by making use of the superposition of mass and the clock rate ticked differently depending on you are closer to the mass or further from the mass to realizing the indefinite causal order. However, there has been long-lasting debates in the community regarding is the optical switch a genuine realization of indefinite causal order and what constitutes the events. So there are many great researchers contributed to the insights of this field. This is an incomplete list and with different opinions. So here we analyze it based on our minimum assumption and this structure we introduced. So we think that to reconcile the debate of optical quantum switch, the different conclusions stem from distinct underlying assumptions of the generalized lab one used to analyze the protocol. So for instance, if we choose the following underlying assumption, the reference is the target label, means whether the target entered my lab or not. And the target considered in the optical switch is the photon without vacuum degree of freedom. And the operation is very general operation conditioned on whether target entered my lab or not to perform the operation. Then we come to the process matrix description. There will be 2 events in the optical switch, and it established the indefinite causal order. And there's also important work show that optical quantum switch can be related to gravitational quantum switch by a quantum diffeomorphism transformation, means they are diffeomorphic equivalent process. However, if we choose the following assumptions, is the reference is the clock in the laboratory that we are performing the experiment, and the clock have enough resolution, and the target is the photon and vacuum. Vacuum means there's no photon come in, which also carries the information. And the operation considered as independent intervention based on the clock reference as the following form. So the identity part is acting on the vacuum. Under this set of assumptions, one will arrive at a fine-grained approach, which was carried out by Villasini here and Renato, and some related to some other authors' work that I didn't mention here. In this framework, there will be 4 events based on this set of assumptions and its definite acyclic causal structure. Moreover, by analyzing it a bit deeper, we can see that under the fine-grained assumption, there is an inequivalence between the gravitational switch and the optical switch. So in order to understand that, we need to introduce 2 important operational properties. The first one is the relative measurability of the reference. So the intuition is the following. I have a lab, I have a clock. Okay, oh, question? Sorry.
Yeah, the question is, so the event would be the unitaries.
Sorry?
The event would be the unitaries.
So in this definition, the condition, the operation considered in the lab can be unitaries, can also be, not.
In your example, it would be the UA.
Oh, yeah, in the example, yes. And so then the definition of the relative measurability of the reference is that given the lab and the initial condition, I can measure the reference and prefer the operation on the target. The result on the target is the same as I just prefer the operation. The measurement does not disturb the outcome of the target. So intuitively, this captures a necessary condition for the classicality of the reference relative to the system of study. Another important operational property is the localization relative to the lab reference. So the intuition is as following. If I have a clock tick the delta t with the resolution, and so measuring the clock, this classical clock in the lab, measure the clock before I'm acting on a photon, before and after that it reads both in T1, and then I can say this operation is localized in this time slot. However, if the clock have entanglement with the target or entanglement with some other degree of freedom, this can get very complicated. And this will not hold. So that's the intuitive example. The formal definition is given by the following cable diagram. So given the lab and the initial condition, if we measure the reference and read out a distinct outcome lambda, prefer the observation, and measure the reference again, this is the equivalent as I just do the operation without reading the reference. Then we would say that such an operation is localized relative to this reference. So a notion of localization, this I think provides a notion of localization without reference to the space-time background because it's only reference to the physical reference frame. And furthermore, the following condition is a necessary condition for the relative measurability, but the reverse is not true. A reference is relatively measurable, but the event is not necessarily localized on it. However, if an event is localized relative to some reference, this reference is definitely measurable, at least in quantum theory. Okay, so now let's come back to the optical and the gravitational switch. The space reference, physical reference for Alice app, if under the fine-grained assumption, which means I can look at the clock in the lab, then they are relatively measurable of the optical switch. However, similar space-time reference, such as acceleration or relative distance from the mass, this is not relatively measurable for gravitational switch. Moreover, most importantly, under these assumptions, Alice can perform independent intervention based on the clock time. And consider including the vacuum, then the Hilbert space structure there is tensor product. However, for the gravitational switch, Alice cannot independently intervene based on the space-time physical reference. The Hilbert space structure is direct sum. And furthermore, in gravitational quantum switch, Alice operation is only relatively localized based on the lab's proper time, which is already in the original protocol. And there's the meaning of non-localization in the both scenario is subtle and different, depends on the relative measurability of the reference. And we have a detailed analysis in the paper that I don't have enough time to go into and you can ask us questions if you are interested in to check out. So in summary, I just pointed only a few future interesting questions. One is that, so whether a distant observer in gravitational switch admits the same operational status as an experimentalist sit next to the optical table in the optical quantum switch. And it's subtle, but we think more or less we have an answer. The second very important question is that now the view is for the individual labs. So this is different with quantum reference frame in the sense of one localized frame in the view of others, but here the localization property is relative to the single lab. So comparing and combining this generalized lab to study the emergence of common notion of events and localization, causality, and the property of space-time would be a very important direction. And this will also involve in combining the tools from quantum reference frames transformation. And the deepest question is that I'm curious the most is how can this help us to understand the regime of genome quantum space-time? Whether there's operational quantitatively inequalities or something could capture the non-classicality of the space-time based on the operational approach. Okay, so now I come to the second topic, which the second aspect of the operational approach. This is quite a different subject. So it's about quantum diffeomorphism beyond the superposition of semi-classical space-time. This is with the wonderful collaborator Flaminia, who just gave the talk. So diffeomorphism invariance is central for general relativity, and with profound implications for nature of time, physical observables, conserved charge, etc. It's one of the key conceptual and technical challenges of why quantum gravity is hard. And this part, if you are interested in, we can discuss more later after the talk. On the technical challenges part, it presents for quantum gravity. So the question we're curious the most is, in what ways does the notion of diffeomorphisms differ in quantum space-time compared to classical general relativity, or in the regime we still have like superposition of manifold, this kind of structure. So these are the important works already established quantum diffeomorphism for superposition of semi-classical space-time. So intuitively, if we think about this question in the first glance, so this is a part of definition taken from the page 10 of Wald's textbook, is that since mathematically, a manifold is a topological space equipped with atlas, which is a family of charts. This is even before the metric, the information of metric comes in. So if one wants to develop the notion of quantum diffeomorphism or quantum coordinate, means one needs to generalize the structure of manifold. So the strategy could be possibly, for instance, develop quantum coordinate transformation which corresponds to passive diffeomorphism. Or we can also develop active diffeomorphism descriptions generated by quantum system. However, eventually, this can be done with quantum system on a classical manifold. Eventually, one want to remove the classical background part, because since the point on the manifold doesn't have physical meaning, and we want to describe observable relationally. So as a first step, we want to look at the linearized diffeomorphism. Even for classical linearized diffeomorphism is still active research field on the boundary charges, symmetries of the space-time, etc. So we want to go beyond the regime of superposition of semi-classical space-time. The first step is to consider a quantum linearized diffeomorphism generated by a quantum system. At this point, this quantum system can be fictitious or physical. So classically, initially, you have classical spacetime with a vector field. And the linearized diffeomorphism transformation on the metric is described as following. This is the classical D field generated by a vector field. And now we want to look at, can we make sense of such type of diffeomorphism generated by a quantum vector field? This is a state of a quantum vector field written in terms of the field basis. And this question can be formulated by one of the initial approach of the quantum reference frame in this paper by Flaminia, Esteban, and Chaslov. So to formulate such a transformation, the concrete system we are looking at is quantum linearized gravitational field. This was based on the previous series collaboration with Flaminia and also Flaminia and Carlo on solving the quantum state of the gravitational field given by superposition of masses or given by more general quantum sources. So the superposition of semi-classical sources give the superposition of the semi-classical spacetime intuitively. However, this is in a regime that the source uncertainty, delta x and delta p, is way smaller than the experimental resolution. So operationally, the uncertainties, the Heisenberg uncertainty for the source is operationally negligible. And in the previous work, we generalized the descriptions to quantum source that such uncertainty is not negligible. And by solving the gravitational Hamiltonian and constraint, we arrived at the wave function of the quantum state of the gravitational field to carry out such diffeomorphism investigation. So such a quantum vector field encoded the information regarding the difference of a quantum reference frame and the initial laboratory frame. Under such a unitary transformation, which is a generalized controlled translation, we can translate it into the frame that is localized for the quantum coordinate, and the laboratory become fuzzy and entangled with the source. And note that one need to assign a Hilbert space for those information. So an important physical point needs to point out that there has been active research on QRF translation from indefinite metric to definite metric. However, to what extent can the quantumness of the gravitational field be accounted for by the quantum reference frame transformation of the classical spacetime? So at least we show that by spatial diffeomorphism, it cannot connect the quantum gravitational source, a field sourced by quantum, generic quantum source, to the field sourced by semi-classical source. Okay, so my time is not enough. I need to go really quick here, is that this can be generalized towards background independent. This is a working in progress. And we can show that the perspective neutral approach of quantum reference frame is actually applicable in this scenario. And one can define relational observables and study the effect of the back reaction of the physical coordinate fields. Okay, now I have about 8 minutes to discuss the third aspect, which is a very exciting project in collaboration together with, in case you don't know, Professor Buchner and Robin. So, in quantum measurements, probability inferred from them are based on the assumption that the ensemble are prepared and measured based on independent and analytical distribution. This underlying the statistical foundation of the state tomography to learn about the state. And then Born rule connects the state we assign to with the observed probability. This enabled us to predict the convergence of the relative frequencies in the measurement of observable. So to make sense of quantum state in the quantum gravity regime, we want to ask the question of how to make sense of tomography and the statistics of the measurement, even if we cannot perform them practically, but we need a notion of conceptually we can define them. Do we have fundamental obstacle? So this needs technically to check the statement, one need to use the relative frequency operator. However, you don't need to be committed to the frequentist to use it to check the failure of IID in certain system. So this is a beautiful idea that developed by Finkelstein, Hartle, etc. And so it's a way to see the validity of probability assignment. So the basic idea is that although individual measurement outcome is inherently unpredictable, however, one can define an operator such that the IID ensemble is the eigenstate of such an operator, and the eigenvalue is the probability of the measurement. And the relative frequencies converges when one have a large n number of the ensemble. In particular, for non-commuting observables, the relative frequency operator commute. So then one can check that if the system does not satisfy IID, this condition could be messed up. So this ensures the probability for all observables are simultaneously well-defined. On the first glance, it seems problematic in quantum gravity. So the first level is the entanglement from the gauge constraint. So by the n copy of identical static quantum source, we can solve the gravitational state, which is entangled the sources. One can check the IID assumption doesn't hold by choosing a set of non-commuting observables. The relative frequency operators also doesn't commute in this case. However, this obstacle can be overcome. Practically in the lab, one can choose the optimal trap to isolate the mass if the mass is small enough, or took them far away enough from each other to have approximate IID. It seems a deeper level when we have an ensemble that can back-react gravitationally, and the energy is relatively large relative to the energy of the whole universe. So one beautiful intuitive example is that if we try to define state tomography for n ensemble of the quantum clocks, they can be far away from each other, but even in asymptotic flat spacetime, you can see from the ADM energy, there's a encoding of the perturbation of the metric from the energy of the clock. And we know from the quantum clock is that if we want the clock to be sharp, the energy gap have to be huge. If we try to define tomography on the clock, the measurement of any single clock energy would influence the quantum state and the ticking rates of the other clock. So the ensemble preparation can be identical, but not independent. So this comes from the second level of the IID problem of quantum gravity. It's the lack of the split property and the back reaction from the universal coupling, which encoded in the previous example already. So related issue also is discussed in this paper, but their proposal is we need to change Born rule. We need to make Born rule dynamical. And here in the last 2 minutes, I can show a proposal that by using quantum reference frame, we don't need to change Born rule and still can have a sense of IID by levitating the tool of this relational approach. So the idea is to reset the reference frame. We start from a local inertial frame called R0, have a quantum state, rho 1, and the observable is relative, defined relative to this frame. After the operation of the first massive state, one need to perform a quantum reference frame transformation to the local inertial frame to carry out the second operation of the second mass, etc. a sequence. And after preparing the massive quantum state, one need to perform the quantum reference transformation to the next step. Then the example becomes the following. The errors indicates that there is a direction in the sequence, and the algebraic property of this is still working in progress. However, then the modified relative frequency operator can ensure that the ensemble is, then the probability can be well defined by every time we initialize the reference frame into an equivalent class. So this is because the correlation due to diffeomorphism, backreaction, and the lack of split property encodes into the correlation among the quantum reference frame at each step. And by assuming equivalence principle holds in the quantum spacetime, this existence of local inertial frame is powerful enough to assume that we can reset to RID for subsystems. Okay, so here is the summary of the lessons, brief lessons we learned from these 3 aspects. And thank you so much for the attending.
So we have time for questions for Lin Cheng. So we just have one right there from Flavio.
Thank you for the very nice talk. A lot of very interesting and very broad different results. I'm interested in the first part, in particular, the way you were distinguishing the laboratory and gravitational switch. Do I understand correctly that your main distinction that you make at some point is whether you can detect locally, with local operations, you can detect the variables that say it's one path or the other path, or one order and the other order. So is it that your claim is that in the optical case, you can always, in principle, detect this information with the local operation? Is that the key difference?
Thanks for the question. So the locality actually come after we specify the structure, the assumption of this generalized lab. And for the optical case, in this distinction, like for the experimentalists, if the generalized lab include like the clock in the lab, etc., those space-time reference have a different property than the physical reference in the gravitational switch.
So okay,
then then the physical reference in the gravitational switch here means, for instance, measuring acceleration or measuring relative distance from the mass. However, within the box, within the lab, the proper time is that will be another reference for the generalized lab.
Yeah, so your distinction is that in the gravitational case, the local observer cannot distinguish which branch it is in. Yes. So in this case, I guess if I were to present you a lab implementation where local operation cannot distinguish, so different from what has been done before, would that change your conclusion? Would you say in that case is at least in some sense more similar?
In optical case?
Well, a new implementation of the switch, which you don't know yet, but where it's not possible by local measurements to detect the branch.
Yeah.
Then you will change the conclusion. Then watch out for the archive in the next months. Thanks.
Thank you.
Okay, other questions? Anybody? Yep, right there, and then Czesław. No, first here. No, right there. He was first, and then Czesław.
I had maybe also about this thing, I have maybe a comment more than a question. One should be careful about including more stuff into the laboratory.
Yes.
Because when we have clock, we have interaction Hamiltonian. And like we can define clocks to be, to interact in weird ways. And then they would discover or recover other things about it.
Exactly, that's a very interesting point. So if my reference have a non-trivial interaction, then these references usually become non-measurable. And then, so to write as a conditional operation, one need to either include another reference that one can write as a conditional operation to define the event, or study this interaction of the reference. So yeah, exactly, that's a very important point.
Okay. And then after, let's get the next speaker.
Yeah, I'm again at the same point, but I just want to say something which I guess clarifies for everybody, that your definition of event is conditional on the lab clock, and you condition on that.
Under those assumptions.
Sorry?
Under certain assumption of choice, if one conditioned on the clock.
Yes, if one can condition. So that means that if Alice would condition her action, but she doesn't need to do this. She can have a clock like we have here, and we usually do not condition our actions on the clock. Exactly. Even then, you redefine the number of events just by mere potential use of this clock. And then I would just remind on on board and making conclusions about non-performed experiments, that is, let's say, at least a slippery business in quantum mechanics.
Mm-hmm. So, if such, so yeah, okay, I need to understand the comments better probably afterwards.
Okay, unless there's a burning question, let's thank Lin Qing again. While Fabio is getting set up, I've been asked to remind people to sign the cost action paper. It's circulating around the room, as I understand it. I don't quite know where it is yet, but please sign.
Tesla will be on.
And this I write it here. So this is for Zoom and this is just for the room, right?
Well, I would rather you use this. Lin Qing was hard to hear. This is for the room and
I will try to shout and see. If they don't hear me, I use that. Okay.
Right, well.
It's okay. No, I handle that, yeah. No. I mean, I'm used to it.
Use this. So.
Yeah, I think I will not actually use it. But
well, I need this to introduce you.
Yeah.
Do you plan on staying on the stage?
Okay, and our next speaker, the last one for this session, is Fabio Costa, who's going to tell us about causal structure, quantum memory, and relativistic particles.
Okay, can you hear me if I speak like that? Or do you prefer that I use the microphone? You can hear me well?
Yeah, but I think the Zoom needs the mic.
No, the Zoom is this one, isn't it?
Okay, all right. All right.
Is it all right? Okay, so if at some point you cannot hear me, tell me, and I use the mic. Okay, so thank you very much. I'm really happy to be here in this wonderful city, wonderful time of the year, with so many wonderful people. Very grateful. And yes? I use the mic, thanks, okay. I'm very happy to be here. Interesting time for me because I'm taking a break from my main activity of this period, which is parental leave, which is very interesting, but it's also nice to take a little break and do some work. That's a partial excuse why the slides are not fully polished. You will not see a lot of references, but there are a couple of references. If you go there, you can backtrack anything else you might need. We'll also take the opportunity, if I may, to also comment how lucky we are to be able to discuss things we like so much and interest us so much in a truly open and international environment. And I believe this is a privilege we should not take for granted in periods like this. Now, as you all know, one of the tools, additional tools we have at the moment to collaborate is the RQI cost action, and I'm particularly involved in working group 3. Now, if you read the title of working group 3, if you read the title of all working groups and all the topics of RQI, so you will see time causality and memory in quantum physics. If I asked you to single out the odd one out of these concepts, I believe most of you will look at that. How does memory fit in RQI? Why is this word there? Well, I put it there. That's why it's there. And therefore, I feel compelled to give some justification. So this talk will be mostly about justifying why this word is there in the action. So if you look at the Memorandum of Understanding, there are a lot of quite interesting ideas and possible fields to explore. So how memory affects thermodynamics, error of time, memory in quantum field theory, all wonderful ideas. I am not aware of essentially almost any work that connects memory with this topic. So these is great things to explore, quite open territories. Now, some things that have been explored So that's typical thing that you do in proposals. Among the things you say you will do, you write things that you have already done. So connections between quantum causal structure and non-Markovian processes. So this is one of the specific aspects that we do know something about. There is work on that, and that's what I want to talk about mostly. To give a little more justification why we should be interested, and it is interesting to consider memory. I will tell you what I mean exactly by memory. Increasingly, we have seen already in this conference, there is increasing use of open quantum system method and tools in RQI. It's somehow unavoidable when you want to get serious about what happens to quantum systems, because quantum systems are not closed. And what you typically see, what everybody typically does, you make some very strong assumption, in particular very strong Markovian assumption, and you try to write down something like the Lindblad master equation. And most of the time, one gets the impression that's the way to treat open quantum system, but we should remind this is, makes sense under some assumption which never hold exactly. Now, we had some discussion. There are some results, actually, that these assumptions are never precise. I don't think there is a very broad theorem that states that, but typically, and the word typical is one, it's very up to interpretation, but typically they are never exactly true. They are approximations. And well, why do we do this approximation? Sometimes we have a good feeling why they're valid, sometimes we don't. The common wisdom is that if you want to go beyond this approximation, things become really, really difficult. You don't know what to do. The perspective I want to give here is slightly different, coming from what I've studied before jumping into this field. Insights from works in quantum causal structure gives us substantial conceptual and formal insight how to treat quantum processes with memory, non-Markovian quantum processes. And in particular, I will argue that in some case, making the Markovian approximation makes things more complicated and not simpler. Okay, what are we talking about? Let's take the stage. Open system, what does it mean? We have a system of interest. Our observers is interested in their favorite system. They want to track some property of interest over time, how it evolves. However, of course, this system is not alone, isolated in the universe. There are some non-accessible environmental factors that affect the system. Now, what I want to focus on is what is the most complete, the most appropriate description of the system alone. What I mean is that, of course, if I had access to all the environment, that would be the most complete description of everything. But assuming I don't, the only things I can do are measure and act on the system of interest. What is the best and most complete way I can describe this? And there is a kind of a Pavlov reaction of, I would say, any physicist, including me. How do you describe a system? Well, there is only one way. You have to give me the state, how it evolves in time. How do you find how the state evolves in time? Well, you have to solve dynamics. And dynamics, what is it? Is evolution from one time to the next time. That's what we always do. I will argue between 80 and 90% of physics is done this way. Probably 99.9% of quantum physics is done this way. And it's sort of my life mission to make sense of this 0.1% and show how significant it is. So, for example, you will find these quantum channels that give evolution from initial to final time as a solution of some kind of master equation, or you can give some circuit model to say what is going on. And then if you want to say what does it mean for this to be Markovian, to be without memory, this evolution, there is actually a zoo of definition. And for someone, the first time you see this coming into this field, this is really confusing. Say, come on, why isn't there a simple, obvious way to say something is without memory? We know what it means. It means the state at this time only depends on the previous time. Why is there Markovian, such a disagreement and a broad variety of definitions? So one of the insights, I believe, comes from causal modeling, causal structures, is understanding why there is this zoo and also what is the actual correct definition. So what does it mean in a conceptually open system with memory? So what are the key ingredients that I believe the picture I just showed you misses when you want to talk about system with memory? We have to talk about multi-time correlations and causal influence. And to make you understand why these concepts are important, I will not start with the quantum case, which is the one is conceptually difficult in a way from the way it's usually presented. I will consider directly the classical limit. So to make some simple example. So what does it mean classical limit? So when we are talking about states, the classical equivalent of a density operator of a state is a probability distribution. And the classical equivalent of a channel is a transition matrix. So the probability to have AT given our variable at some point, at some time, given the variable of the previous step. So these are the classical equivalents of these two concepts that we instinctively want to use to describe evolving systems. And I will give you some example to show you that arguably these things are not enough. Well, I mean, these, you can very easily prove that these are not enough in classical stochastic processes. So multi-time correlations. I will give you a very simple example of a work with memory. So our variable of interest is binary, can take values -1, the worker goes to the left, and +1, the worker goes to the right. So in this case, I take as a variable the direction and not the position, just for the example. And so the work works in this way. The first 3 steps are random. I toss a coin, and I either go left or right with probability 1/2 for the first 3 steps. But now from the 4th step, what I do is I look at the previous 3 steps. I look where I was going most of the time, and notice I chose an odd number, so it's always either one way or the other, and then I go the opposite way. And so, for example, I start walking, I draw the first 3 at random, right, right, left, and then I look, okay, I went twice right and once left, so this means I have to go left now. So notice this is a completely deterministic evolution. And so I go left, now I look back, twice left and 1 right. And you see this is a very, very simple process, kind of boring. You're trapped there. You see whatever are the 3 initial states, you will be trapped within a very, very confined region. So I would say very, very simple to understand. However, let's say I want to ask you what is the state of the system at a given time. And state, I don't mean the particular left or right, I mean the probability to go left or right, and that's 1/2. And if I ask you what is the transition probability, it's also 1/2. So if I just look at this state and transition probability, I cannot distinguish this process from a completely random walk. If I want to distinguish, quite clearly in this example, I need to consider this multi-time correlation. So I have to consider the probability for A. I mean, that's exactly how I set up the situation, but I'm trying to convince you that in this case, you really necessarily need to look at the transition probability from a number of previous steps to the current step to see the presence of memory. So, okay, point number 1, you really need to talk about multi-time correlations. Okay, so now we're talking about classical processes. So is this surprising? Is this known for classical stochastic processes? And what are classical stochastic processes anyway? So we're lucky that here there is a very broad and well-established theory. And I will not, I mean, mathematically it can be very complicated, but let's focus on the concept. Essentially, a classical stochastic process is a probability distribution over histories. So it's a joint probability to have A1 at time 1, A2 at time 2, A3 at time 3. It's the whole joint probability. And in this context, one defines some condition that is called the Markov condition, which is that this probability factorizes in this way. You can write this probability as the product of the 2-time marginal, an given an minus 1, n, and so on. So in this context, it is true, if your process is Markov, it is true that if you have the initial state and all the transition probabilities, then you can reconstruct the whole process. So in this case, you can make sense of our typical intuition of a state evolving in time, and not by chance. These are the most lattice processes, because you can do a lot of things, a lot of mathematics, a lot of manipulations that are very familiar. You write master equations and things of this type. Now, what I want to stress, this is a condition, and it's not satisfied in general. And of course, we're interested in exactly in those conditions, situations where it's not satisfied. And now, coming from this, we could start to ask, okay, so then what should we do to write a quantum stochastic process? If you look at this a little naively, it immediately gets confusing, because I told you that a probability distribution is the classic analog of a state. So now we have a joint probability distribution. Of course, we should write some big joint state. But this is a problem, because in quantum physics, the way we learn it at school, which we don't learn it right, in quantum physics, the state is at a given time. You don't have such a thing as a state over time. In the ordinary formulation, it really does not make sense. And physically, the origin of this, or one way to think of the origin, is that if you want to look at this probability, this multi-time correlation, you need to go and measure the system. But in quantum theory, you cannot just passively measure the system. Anytime you interact with the system, in the usual story, you collapse it, which is a very mysterious thing. Now, the core of it is that the measurements disturb the system. You cannot avoid it. So this means that you cannot just consider observation. You must include active interventions, which brings to causal influence. Causal influence is essentially correlation between something you observed and an active intervention. So this is why it's so difficult, if you start from this kind of naive perspective, to generalize classical stochastic process to quantum ones, because classical stochastic process usually don't include active intervention in the usual formulation. And now I want to give you another quick example. I didn't start my timer, but I guess who is keeping track of time? You're keeping track of time. Yeah. 12 minutes. Okay, so a very simple example, maybe I will go quickly, but this is an example that is fully deterministic, where you don't see the effects of memory by observation alone, but you can see them with intervention. So very, very simple case, your system is, your variable of interest is just the temperature of a system, and it's coupled to an environment which is just a bath, but of finite size. Now, if you just look at the temperature, the only thing it can do is decays, the thing thermalizes, and so it goes exponentially down to the equilibrium state, and it's fully Markovian. It's easy to convince yourself this is a fully Markovian evolution. You're just observing. Now, assume I can do an intervention. I can go and change the temperature. For example, I take away the box and I put another one with same properties but different temperature, just as an example. I can do that in the lab. Now what happens? So I start my evolution, my system starts to thermalize, and then at some point I raise the temperature, it starts to thermalize again, but my bath was finite size, so what I did not see the first time is that while my system was thermalizing, also the bath was thermalizing, which was changing temperature. So when I put the new system with the new temperature, now I'm thermalizing to a new equilibrium temperature, which depends on the previous temperature there. So in other words, the environment, my thermal bath, has memory of the system, of the property of the system that was interacting with before. So if you do interventions, you can determine that the bath is finite size. You can determine that it has memory, while you cannot see it if you don't do interventions. So the memory in this example is only visible through interventions. So this means we also have to modify a little bit the classical story if we want to include interventions. Now, very briefly, there is a whole field called classical causal models. I will not spend a lot of time. You also want to talk about more complicated structures, not just a chain of events. What I want to bring is that one of the key things you do in classical causal models is to explicitly take into account interventions. Otherwise, you cannot really talk about causal orders. And there is something called the causal Markov condition, which I will not talk in detail, but it's something that is very similar to the usual Markov condition, but includes interventions and causal influence in that. So again, the particular informalism is not important. It's just some insight we can gain when things are non-Markovian. That's essentially when there is some influence, some causal variable, some causal node in the graph that is not observed. So latent or non-accessible nodes, or in a way, an environment that mediates the causal influence between a time and the later time. So intuitively, I do something here, information goes to the environment, it can come back. It's not always like that, but things of this type. And you can analyze, you can use these concepts to distinguish different types of causal structure. Now, we'll probably have to go a little quickly if we want to go to the end. So, okay, with all this inside, we can introduce quantum stochastic quantum processes, which we can call stochastic. Maybe we should call them causal. And essentially, we have to take into account multi-time correlations and intervention. And this is, in fact, as we said, in quantum physics, as soon as you talk about multi-time correlations, you naturally also talk about intervention because you have to specify the choice of operation you make. So operations are described as completely positive maps, as usual. So just to highlight, at each point in time, to describe an operation, you need a transformation from a Hilbert space to another Hilbert space. Typically, we think they are isomorphic, but we use this particular tool, which is the Choi-Jankowski representation, that represents one operation as an operator on the tensor product. So now this operation or measurement that you performed is sort of the same status as measurements or states. It's just that it's a tensor product of an input and an output space. And a quantum process is described by something we call process matrix. So you have heard a few times in this conference, but just to give you the really basic of what it is, it's an operator in the tensor product Hilbert space of input or output of each time. So even if you have a single qubit, but you observe it multiple times, then you have to introduce 2 qubit spaces for each time. So it starts to become a very large space, but that's what you have to do to consider all possible multi-time correlations. And the conditions of the operator is that it's positive semi-definite. So it actually looks like a state over time that we said was not possible, but it's not a state. And the reason it's not exactly a state is that you have to impose linear constraints to avoid causal influence from the future to the past. And if you want to calculate probabilities, you have something called the Born rule, which looks exactly like the ordinary Born rule, except you put, instead of states, you put these process matrices, and instead of POVMs, you put the Choi representations of your channels. So the good news here is that the mathematical structure is really similar to what we use in quantum information. So if you have a favorite concept that you use for multipartite states, you can directly see what happens to it in the process in the multi-time case. If you have a multi-time entanglement, multipartite entanglement, phase transition, you name it, you can go do this process and see how it looks like there. It makes sense. And just to say, and I said I'm not really citing everyone I should cite, but this idea has been derived and rederived many different times, so it has many different names. And to say that you can generalize these constraints on the process matrix to explore even weirder and more exotic situations that I will not really discuss here. But just to say that's, in fact, we started looking, at least I started looking at more exotic situation and then came to this. And now to remind, now that we understand what is a process, it's defined as this process matrix. Now we can define this property of Markovianity, which is really simple. It means the process is a product of a state at the beginning and then a transformation between a time and the later time. So as we expected, and it was the case in the classical case, if you have the initial state and then all the transition, so these Tj are the Choi representation of the channel from a time to the later time. Given these, you can reconstruct all the statistics, everything you want. That's what it means Markovian. It means that the evolution between each pair of time steps is independent of each other. And then the next step, coming to a bit more recent results, what you can do within this framework, you can start taking insights from what you know about the multipartite states and from causal models. You can classify different types of memory. For example, you can say, well, I have something that is not Markovian, so that it's not a product, as I said, but maybe I can simulate all the effects of memory with some just classical randomness that in general will have to be exchanged time by time with the system. And the even more particular case I want to focus on is when actually there is a single random variable that decides all the evolution. So essentially what we have here is that we have a set of Markovian processes that depend on a parameter. We have this parameter nu. If you know what is the parameter, then you just have completely Markovian evolution. However, you don't know this parameter. And we call it classical common cause because you can think that this is something that is set at the beginning, and the effect of memory, it's only due to this classical common cause. You don't know what it is, but then the process has this very simple structure, which is a convex mixture of Markovian processes. Yes, 5 minutes. OK. And then I will quickly jump to the results. So in particular, recently we got interested in connecting this with more traditional open system modeling, where you use an Hamiltonian to have interaction between system and environment. And the main question, can we relate the Hamiltonian with types of memory? And for this case of classical common cause, there is a very simple characterization of the Hamiltonian that gives you classical common cause, which are quantum-controlled Hamiltonian. So if the Hamiltonian has this form, then you're guaranteed that your evolution is a mixture of unitary evolutions. And this is the situation where I will say a mixture of unitaries, if you know how to solve and how to model these unitaries for each nu, then taking mixture is not really a big deal. On the other hand, if you try to take this Markov approximation and write a master equation for this stuff, first of all, you don't know if it will hold or not. And second, things might start to be extremely complicated, even if the full picture is quite simple. And just to flash something that is not published, but it is nonetheless true. If you take one of the typical situations, one of the things that is studied in relativistic quantum information was mentioned already before. You take a relativistic particle with internal structure, and the internal structure works as an environment here. You're interested in seeing how, say, the interference of the external degrees of freedom. Then it turns out, maybe I will not detail, but from very basic mass energy equivalence principle, you see that if you want to write an Hamiltonian, necessarily it needs to have this quantum controlled form. Essentially, for each energy, internal energy, you have a definite mass, but if you have a superposition of internal energy, you have to consider this Hamiltonian, which means the reduced dynamics, even the multi-time dynamics, can be fully captured by these mixed unitary models, classical common cause models. So maybe I will just put my conclusions here so that you can read them while we take questions.
Okay, thanks, Flavio. We finished a bit early. We have time for questions, and I see one over there.
Was this up to question time or up to the end?
Well, you were a little bit early. You had another 2 minutes, but we're in it now. So.
Thank you very much, Fabio, for the really interesting talk. I like a lot that you combine insights from different areas of quantum causality, especially causal models and process matrices. So one question I had is in particular regarding the relation between how you define memory and non-Markovianity. Between memory and non-Markovianity.
Yes.
So in particular, does your definition of memory require some notion of time or definite causal order? Is it only defined for combs, or is it make?
Does. So the one I've showed does. There are works generalizing to things like cyclic causal model. Now I've only talked so. There is quite some literature on quantum causal model, so generalizes this classical causal model framework. The additional ingredient there is that, so let's say the story I'm telling you is about the simplest situation where you're interested in a chain. In the more general structure, you're interested in all the DAGs. So different approaches all coincide in the definition of Markovianity in the situation I've shown, but they differ a little bit in the more general case of DAGs, in the way you define the causal Markov condition for general DAGs. And so those works on cyclic causal models, they start from those other definition of Markovianity where things are not exactly in the tensor product. So the short answer is what I showed is strictly for time order, but there are works on extending to not causally order, and I think more can be done in that context.
Thank you. Yeah, I'm aware that, as you say, that's very interesting literature to define non-Markovianity for the cyclic case.
Yeah.
But would you say non-Markovianity and having memory are somehow equivalent?
In the context
that's what I would like to understand.
So in the context of classical stochastic process, they're kind of synonyms, and that's how I take them as synonyms here. Yes, I didn't spend a lot of time thinking deeply what memory means. I just take it as equivalent of non-Markovianity for time order things.
Okay.
I think there is space to discuss what actually memory means. Like, is it really what we understand as memory completely equivalent with what we understand as Markovianity? Should we make some distinction? This is another topic that will be interesting to explore.
Thanks, that's very clarifying. Yeah.
Okay, other questions? Yep, right there.
Thank you very much. You formulate your idea in the language of mixed states and density matrices. Can you formulate it in the language of unitaries and pure states?
I can. There are different levels of that answer, but let's stick to this simple causal order case. If you go to the non-causal order, the things start to be quite broad in this case. If you stick to pure and unitary, then you're always Markovian, essentially. So yes, you can, but then yes, it's just Markovian. So that's also why often non-Markovianity is just considered as a very complicated type of noise, because it is some kind of non-unitarity. But I'm arguing, I mean, that's not only me. Non-Markovianity is a very structured noise. So actually, you can use non-Markovianity. So if you know that your process is non-Markovian, you can actually use this information to, say, have better protocols. You can recover information that otherwise will be lost. You can optimize your things better. But yes, so in this context, non-Markovianity only appears for density operators and open systems. Yeah.
Okay, let's thank Fabio again. And we have